All right. Can everybody hear me? Good? All right. So my name is John Kubiatowicz. As you heard briefly, most people don't call me Kubiatowicz because they can't pronounce my last name, so most people call me Kubi, but that's okay. Today I'm going to basically take you through a lot of setup material for the rest of the course. We're going to talk a bit about hardware. We're going to talk about why parallelism is suddenly so interesting to so many people, even though it's been around for 30, 40, 50 years. We'll talk about some hardware. We'll talk a little bit about some programming techniques like Pthreads, but not too much because you're going to get a lot more of that in the rest of the course. Okay? So let's start with a little bit here. You know, the world is a huge parallel computer right now. I'm sure you're all aware of that. We've got everything from huge server farms spread across the globe, all connected with cell phones. You've got lots of devices in cars. In theory, things are becoming more networked. I actually found a few networked refrigerators and so on, although I'm not entirely sure what the use of surfing the web is while you're getting milk for cereal, but why not? So the real question is, why is parallelism, which has clearly been around for so long, suddenly very interesting to everybody, and why are you guys here, other than our great personalities? And I think it's really because parallelism is being forced at the lowest level. Okay, all of a sudden, every chip that is coming out has the potential to have more than one processor on it, maybe two, maybe four, maybe 100 of them. And that kind of changes the game because server-level parallelism is pretty easy to get. If you've got 6 billion people all doing a search, that's lots of parallelism, no problem. On the other hand, if you've got some I don't know, PowerPoint, for instance, and you've got 100 processors and you want to try to run it, that's a whole different story. Okay, so it's really about the parallelism down at the lowest level that kind of brings us all together today. And in case you weren't aware of it, the future is now. This was an experimental chip back in 2007 from Intel that had 80 cores on it. Here's a more recent one that has only 48 cores, but it's got a lot more interesting sort of hardware wrapped around it. And probably none of you have purchased a laptop in the last couple of years without multiple processors on it. Okay, it's just kind of the way it is. So let's get some terminology to start today. So what's many core mean? Well, 64, 128, I don't know. Let's say somewhere in that range. So if we're talking about many core, we're talking about 64 processors. Okay, and that's a target that some people think will be reached commonly. Okay, now there's been some very interesting arguments about that recently, and we can do that offline. But let's suspend enough disbelief here to think that we might have 128 cores on your cell phone or something in the near future and go with it. Okay. So how do you program this? Well, if you got a desktop, clearly you use 2 CPUs for video and audio. You got one for your word processor, one for your browser, and the other 76 processors are all busy doing virus checking. Okay. All right. Now, hopefully we can do better than this. All right. But this is the obvious thing you might imagine. And the problem is that a lot of the stuff that you and I care about on the client isn't very parallel up front. And so clearly we need something better. All right. And that's what this course is about. It's going to be throughout the whole next 3 days, that you're going to learn different ways of tackling parallelism and hopefully leading us toward that future where we can use 128 processors easily on a portable device. Today, like I said, what I want to do is pick up some common terminology that will be with you for the rest of the course. We're going to talk a bit about uniprocessor parallelism for those of you that are not aware of it. You've actually been using parallelism implicitly for a very long time, probably every one of you. And the only reason we're in this mess now is because the options there kind of ran out. And so the programmer could no longer ignore the fact that the underlying hardware was parallel. Okay, and I'm going to tell a little bit about why that is. And then we'll talk about some parallel computer architecture, programming models. We'll talk about shared memory versus message passing. We'll talk a little bit about synchronization, Pthreads, etc. And finally, time permitting, we might actually dive into some parallel machines. I have sort of a zoo of possible things to show you at the end, but we'll see where we get. Okay? This kind of a lecture is sort of fluid depending on the audience. Okay. Feel free to ask questions if you have them, okay, because this is intended to be interactive. So, everybody with me where we're about to go? Okay. So, let's start with computer architecture. So, computer architecture is not about hardware exclusively. Okay, I don't know if how many of you have taken an undergraduate computer architecture class? Okay, you probably spent all your time on pipelines and things like that, right? Well, we're going to talk a bit about pipelines, but the point I want to get across at the very beginning is it's not just about hardware. I like to call this the VAX fallacy, okay, which is what you do to make a computer perform well is you make your hardware do exactly what you need. Like, for instance, you produce a single instruction that does polynomial multiply. All right, that was actually a VAX instruction in their heyday. And the reasoning was, well, you make the hardware fast, everything else runs quickly. Okay? And the problem with that, of course, is that to make that polynomial multiply work well, you end up making the design more complicated, so it's harder to debug. You make the design more complicated, so it's slower. And the net result is it's slow. Okay? So this is not the right thing to do. In fact, there was what I would like to call the risk philosophy, which is you need to look at the whole picture. It's not about what any individual component's doing. It's about the whole picture. Notice the programmer in a typical day-to-day situation is dealing up at some very high level, maybe even above the compiler. Okay, a lot of the stuff that you might encounter in your parallelism is really going to go through some source-to-source transformation from language A to language B, and then through a compiler, and then it gets linked with a bunch of libraries, and then it interacts with the binary and dynamic libraries that are actually on the system and the operating system and maybe a hypervisor, and there's some hardware underneath there, all right, but it's not the full picture. And if you ignore that it's not the full picture, you get the wrong answer, and that led Digital Equipment Corporation down a bad path there, okay? Not to say that they weren't a great company. So modern programmers also don't typically see assembly language. How many of you have programmed in assembly language? Ooh, we have some brave souls out there. We won't force you to do it today. How many of you programmed in C? Okay, that's better because I'm going to use some examples that are C-like, but C is glorified assembly language, and hopefully you won't be forced to do anything too complicated in C either. Okay, but that's where we're going here. So we're going to try to get the big picture here. And, I'm not going to go in this. If I were taking my undergraduate architecture class, I'd say, look, the way you don't fool yourself is you measure. So there's some famous equations. For instance, CPU time is, number of instructions per program times cycles per instruction times seconds per cycle. There are three separate pieces here. You can optimize them individually. If you make really complicated instructions, you might reduce the instructions per program, but the seconds per cycle goes up so much, everything's much slower, okay? So the way you don't fool yourself is you have metrics for success and for measurement, okay? So always keep that in the back of your brain. Amdahl's law, another good example, right? How many of you have sat down with a program and you said, if I only sped up this one little thing in the middle by 1,000 times, I'd be faster? How many of you have gotten into that loop? It's usually at like 3 in the morning, right? And that 1,000 times faster, the problem is, here's a good example. If this green thing is 1/3 of the total execution, I make it much faster, I still haven't sped up the whole thing very much, right? And in fact, if this fraction was, say, 30%, the best I can do is speeding everything up by 1.5, even if this was infinitely fast. Okay, so these are all, I'm not going to dwell on this, but I just want to make sure we set the stage that you need to measure ultimately in some way to know whether you're doing better. Okay, so now let's talk a bit about uniprocessor parallelism. So parallelism's everywhere, of course. Modern processor chips are bordering on 1 billion transistors, okay, no problem. Okay, that's a lot of individual little devices that somehow must be working together in a way that is useful. Okay, if you've got 1 billion transistors doing nothing but burning power, you're basically melting your laptop. Okay, so you got to use these 1 billion transistors carefully. Now, how do uniprocessor architects extract parallelism? Well, up until about 2002, and we'll talk about that in a second, what happened was people at Intel, people at AMD, people at Sun Microsystems, what have you, all worked on making those transistors give you the illusion that you're running in serial, but really doing things in parallel. So they'd implicitly extract parallelism underneath, figure out which instructions could be reordered and so on in a way to make these billion transistors do something, it wasn't a billion at the time, but make them do something useful and not let the programmer worry about it. Okay? Now you can imagine how far that went. Well, I already told you, 2002. Okay, and somewhere about 2002, sorry about that, it started to run out of steam. And I'm going to show you some very clear slides a little bit in about 15 minutes that show you what happened. But this was great in theory, and it didn't work out. Okay, but it really worked for a long time, 20 years. So it's hard to say that something that worked well for 20 or 30 years didn't work out. But it's not working anymore. And what are some examples of this ILP? Now, this is instruction level parallelism. Okay, pipelining. Okay, you probably all heard of that. I'm going to review that briefly for you. Superscalar execution. More than one thing at once launched together. VLIW. Explicitly letting the compiler say what's happening in parallel. Vector processing. That's making use of things like linear algebra, which has a lot of parallelism just implicitly by the specification and building hardware to do something with it. Out-of-order execution. You take something that's very long and you bring it off the critical path so the things that are fast can go quick in front of it. Okay? You've all heard these terms probably. I'm hoping by in about a half an hour or maybe 45 minutes you'll have a very good flavor for what they mean. But what's pipelining? This is my favorite undergraduate slide, so you guys get to go back to undergraduate for a little bit here. You all did pipelining when you were an undergrad, I hope, because you probably all did your laundry. But, you know, the way you get something to work well is you have a load in the washer, a load in the dryer, and you're folding a load kind of in parallel with each other to get a parallelism of 3. If you did if you did a load, wash, dry, fold, and then the next load, wash, dry, fold, you're there for a long time, say 6 hours in these numbers I've given you. If you pipeline it, you get 3.5 hours per load, which is a much higher, well, almost a factor of 2 in improvement. Okay? And, you know, you could talk about the bandwidth in loads per unit time, okay, if you're, right? And pipelining here clearly helps the bandwidth. So in other words, rather than a load every 6 hours, I'm getting a load every 3.5 hours. But it's not improving latency because to get an individual load through actually takes longer than it did before. Okay? And you could say, well, this bandwidth is limited by the dryer because that's the slow piece and so on. Okay? So the potential speed up here is a factor of 3, but if you actually look at what we got, we ended up with a factor of not quite 2. Okay. So, you know, you're in your class and you go on to MIPS pipeline, right? So here's a simple 5-stage pipeline where you pump instructions in, you decode them, you look up their arguments, you execute, you possibly do a memory operation, you write the result back, right? 5 stages. Possibly a speed up of 5. So this was a lot of pipelines that were of the RISC style up until, I would say, the early 90s. Okay? At which point people started putting more than one instruction at a time down here. Now, we're not going to go into the details of this. That's for an architecture class for you guys. But for instance, you can kind of look at diagrams like this where you see sort of here's the instruction fetch, the decoding stage, the execute, the memory, and the write back. That's 5 pieces of a given instruction. And while one of them is fetching, the next one's looking up its arguments, right? And so if you look at a slice in the middle here, you have one instruction fetching, one looking up its arguments, one executing, another writing back to memory, and so on. Okay? Simple. Ideal case, you get one new instruction per cycle is popped down here, right? So here's a new instruction, new one, new one, new one. Superscalar, you have more than one instruction fetch. Okay, so we got all those terms to everybody. Anybody have any questions on that? So pipelining is kind of an obvious style of parallelism that architects have been aware of since the beginning. Okay, that's been around a long time. And does anybody know what happens to this idea? I mean, why can't I just put smaller and smaller units of work here, more and more stages, lots of things overlapped. I mean, why does that not just solve the problems? Okay, branches. What else? Data dependencies. What else? Yeah, overhead. You know, if I turn these 5 stages into 100, then the latches, which are these little thin green things, become the major part of the computation, and you're doing nothing but moving things from point A to point B. All right, so you guys are clearly on top of it. So what happens? Overhead. Hazards, okay? These are things like structural hazards. Gee, I needed 2 washing machines, but I've only got 1. Okay? Data hazards. This is one that you didn't mention. This is a case where I need a value before it's computed yet. Okay? If you can imagine putting 12 instructions in parallel, it's possible that one of them depends on the other one and you got problems, right? And then control hazards are actually one of the biggest problems, which are the branches somebody mentioned. And so superscalar tries to put more and more instructions simultaneously, and it just makes all this worse. So in some sense, what the architects were able to do with their billion transistors up until about 2002 is they were able to shove more and more things together in parallel, more pipelining, more superscalar, a little more out of order execution, which was a big deal, and I'll show you that in a moment. And they were able to hide the fact that parallelism was going on from the programmer. Okay? Like here's a data hazard example where you do a load. Here I'm loading into R1 and then I'm subtracting using R1. So there's a little assembly language, wake you up in the morning. And notice the problem here is if I pipeline this, the load value is not available till here, but it needs to go back in time, okay, in order to be used. And unless you've got faster than light logic, which is cool, but non-existent, going back in time is hard. Okay, so the best you end up doing is stalling. Okay. So let's say a little bit about out-of-order execution. I want to make sure we have all our terms available here. So here is a case where we have a divide, which in this instance is long. It's producing F0. It's feeding into the add. We have a subtract that doesn't have any registers in common with this. Okay, now a standard traditional pipeline would do the divide, then the add, then the subtract. Because that's the order the programmer said, then clearly that's the order we better do it for correctness. Except, if you think about it, this subtract has no dependency on either the divide or the following add, so why not do the subtract before the divide or in parallel? Why not? Maybe we get some speed up there, okay? And so out-of-order execution is that process of rearranging the instructions to try to make sure that the slow ones don't hold up the fast ones. Okay, and a good example of slow, by the way, is not just divide. Something like a load that cache misses is a slow thing, and we'll talk about caches in a little bit. So, and the other thing that's interesting is if you execute things out of order, then you're going to end up completing them out of order. Okay, and of course, that ends up with all sorts of problems, like a precise interrupt issue. If you want to try to get a clean stopping point, you run into all sorts of messes. And here we have some examples here where the multiply takes a long time, and it's feeding this divide, and there's a read after write hazard, and we have to somehow stall a lot. Okay, this is an example where something feeds into something else, and the pipeline's busy causing things to wait, causing them to go faster, causing them to go earlier. It's complicated. It's fun. I mean, if you're a computer architect, it's great to put these kind of things together, but it's hard to get right, and ultimately, it burns power, and at some point, you get a vanishing point where it's really hard to do this anymore. Okay, remember that number 2002, right? That's a year that this stopped working. So here is, just to toss this up, here's a famous organization from a guy at IBM, Tomasulu, where what you did was you took all the instructions and you fed them into these reservation stations by on the fly analyzing the data flow order. So you take all the instructions, you figure out who depends on what, you resort them, you put them in buffers so they only fire and execute when they're ready to go forward. And as a result, you get complete out-of-order execution, but when something depends on something else, you take care of it. Okay? If you took a class with me on architecture, we'd explain this to you more clearly. I won't go into it in more detail except to show you these little red lines here, for instance, what happens there is when a multiply that somebody depends on finishes, it broadcasts its results to the registers and anybody else who needs them, and we go forward. So this is a general structure that's used by most of the computers you guys will buy today that has something like the Tomasulo organization, reorders all the instructions, executes things out of order for you. Isn't that nice? Okay? So what does a modern processor do? Well, fetches 6 to 8 instructions per cycle. Pipelines are tens of cycles, sometimes 20 cycles deep. Lots of overlapped instructions going on simultaneously. Oftentimes you do some work, but then you discover you did the wrong work. That's speculative execution, so you throw it out. Okay? So here we go. You ready? Grab a bunch of instructions, determine all their dependencies, eliminate dependencies whenever possible, throw them all into the execution unit, let each one move forward as its dependencies are resolved, and appear as if it's executed all sequentially so you don't confuse the programmer. Okay? And of course, hazards are the biggest problem, and you probably need to guess. So this is things like speculative execution, where, for instance, branches, which might be 1 every 5 instructions, when you're fetching 6 and 8 instructions simultaneously, you got problems, because you need to know where the next instruction is before you've computed the result of the branch. So what happens is people guess. I think the branch is going to go this way. And it works pretty well. 90%, 95%, 99% of the time you can guess. Okay, and so these predictions are great. What happens when you predict incorrectly? Well, you got to throw the results out and you burn power. So this speculative execution, fundamental part about getting parallelism out of uniprocessors, burns power and has started to cause some serious problems. Okay? By the way, it works. Okay, architects are pretty smart people. They are able to make it be as if when you guess incorrectly and you executed 10 instructions as a result that those 10 instructions never happened. They can make that all work. Okay, so you should, if you're a computer architect, you should pat yourself on the back. Okay, but working and being the right thing are not necessarily the same thing. Okay, complexity, very complicated. Again, architects get to pat themselves on the back because they're able to take this complexity and produce things that work. Okay, mostly the laptops that you guys buy and the cell phones and all that sort of stuff have working processors in them. Okay, I actually, when I sit back and I look at what it is that's involved in making a modern processor work, I'm always amazed that it works. It's very complicated. Okay? Now, here's an example of a very simple, relatively simple, out-of-order execution machine. I just wanted to put up the power 4 so you guys see what we're talking about. Here's a pipeline. Notice here we're fetching instructions. 2 fetch cycles because the cache is long. It takes 2 cycles to fetch things. Here's branch prediction. We have this loop. What it's doing is it's busy fetching instructions by guessing the branches. Okay? That's not limited by the actual execution, which is way over here. So this branch prediction thing's just doing it, you know, predict, 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 predict. Okay? Yeah, we actually do execute the instructions where we toss instructions down this pipeline and we crack them apart and we decode them, and then we have 4 different pipelines that can be running in parallel. You know, some of them computing branches and some of them doing memory ops and floating point and so on, and then the results come back and, oh, yeah, we actually check whether we got the right branch prediction or not, right? I mean, I suppose you have to actually eventually compute your branches and see that you did the right thing. Okay. That all works. All right. Unfortunately, here's a fun little graph. So let me interpret this for you. So 100% is all of the clock cycles involved. This is an 8-way out-of-order superscalar processor simulation. What you see here is where do all the cycles go? Okay, and as you might guess if you stare at this for a little while, what's down here in black is actually useful processor cycles. What's all this other stuff? These are hazards. Branch mispredictions, long operations that get in the way. Okay, so you tell me what fraction of our cycles and therefore power that we're burning are actually being useful here. It's not very high. Okay? So, you know, you run this thing really, really fast, you burn a lot of power, and it melts a hole through your lap. Okay? Are there any questions on this? I'm going to show you this graph in a little bit again when we talk about multi-threading, because there is a little bit of way around this, but not a lot. Okay. So, all right, that was your brief introduction to some uniprocessor things. So we're all aware of Moore's law, right? How many people know about Moore's law? How many people think Moore's law has something to do with performance? Okay, well, clearly it must, because, you know, people talk about it at the same time they talk about performance. But in fact, it doesn't have it's not directly about performance. It's about number of transistors on a chip. So Moore's law says that basically you get about 2x transistors every 1.5 years or so. Okay, and everybody who talks about the demise of Moore's law, and it happens over and over again every decade, has not been right yet. Okay, now, yeah, we're getting down to where transistors are getting close to the sizes of atoms and so on, and that's a problem. Okay, but by and large, we've been growing on this log linear curve, for a long time, where this is linear in time, log in number of transistors, we get a straight line, and the number of processors in a chip has been growing exponentially for a long time. Now, if you're an architect, that's kind of cool, because it means that the building materials you get double every, 18 months. Okay. Here is another graph that's more what you're used to when you hear Moore's law in the news or whatever, and that's because the two get confused. This is a graph of performance as a function of time. Again, log linear. Here's the log part, linear. It's basically on a straight line from about 1986 up to 2002. We got a doubling in performance of processors every 18 months or so, right? So this was the mantra: if your processor is too slow for your application, wait a little bit and it'll be fine. Okay, this is an amazing thing about the computer industry. It kind of led, I don't want to say it led to lazy programmers, but you could kind of think of that. Well, I'm not very efficient, but it's okay, it'll be fine in a year. Okay? What's interesting here, however, is this. Okay, right around 2002, suddenly we took off at a much slower rate. And why is that? Why did we? So the performance was no longer growing. Why? I think this is a pretty dramatic curve there. I should get newer data and follow this out to 2010. By 2006, which is 4 years off of 2002, we were already 3x down from the expected performance. You can see things were kind of falling off here. Why? Power. What else? Actually, let's put up power, because I think this is fun. So here is a power density curve. So this is, if we were to follow Moore's law and keep every transistor in action all the time, okay, and here's sort of a log linear scale again. Notice that the density, which is sort of how much heat per unit area, kind of very rapidly gets up to something like a rocket nozzle, okay, by 2007 or something. And I don't know about you, but a rocket nozzle on my lap while I'm working on my slides is not exactly what I want here, okay? So power became a really serious problem. You can't take every transistor you get and use it all the time. Okay, what else is the problem? Yeah. So complexity leads to what? Okay, complexity leads to inefficiency. All right. Now, I actually think that that's one of those things that you could state it in a way that is often true, but not always true. But yeah, okay, complexity often leads to inefficiency, which may make things run slower than you expected. Okay, what else? Speed of light got in the way. Capacitance got in the way. There you go. Yeah, so one thing here, so here's a curve, by the way. Let's all appreciate this graph. Ooh, ah. What you see in green here is on a log linear scale is transistors. Okay, growing pretty happily. What you see in dark blue here is clock speed. Okay, so one of the things that was really nice in this early time here is the clock speed was growing exponentially. And so clearly things moving faster, that's great. Okay, but notice that somewhere around 2002 the clock speed started falling off because of complexity, because of power. If you run things faster, they get hotter. Okay? And so basically, notice how it's kind of asymptoting, right? I remember how cool it was to, oh, I've got a 100 megahertz processor. Well, I got a 220 megahertz processor. Well, I've got an 800 megahertz. Well, mine goes a gigahertz. Now it's been stuck at about 3.5 gigahertz for a long time, right? In fact, it's going up and down. And yeah, you can find something pretty high, but it's not really going anywhere. And also ILP, which is that ability of architects to transparently find the parallelism underneath, hide it from the programmer by launching many instructions and executing them out of order and speculating and throwing out bad results and what have you, fell off. Okay, people hit the limits. You can only do so much of that. Okay, and so I think I like this graph because this is pretty dramatic. By the way, this is power. Can anybody tell me why power asymptoted? Huh? Well, actually, leakage is a reason that power would keep going up. Why does the power graph, these are for real chips, why does it asymptote at about 100 watts? Yeah, that's about the best you can cool easily, okay, at 100 watts. With beyond 100 watts, you start having to have very esoteric things. And I know there's probably some of those of you in the audience who say, well, I can do 150 or I can do 200 watts. But, plus or minus 2, it's pretty hard beyond that, okay? So what is this leading us all to? So our first little half hour of this class has kind of led us, hopefully, to this notion that, yeah, there's parallelism you can discover underneath, but we've really run into a wall. And there are many walls, by the way. People talk about the memory wall. We'll talk about that a little bit later. There's the power wall, which is basically you can't cool anymore. There's kind of this clock wall where you can't go any faster. And that has, by the way, this clock speed thing is not just power. It's also capacitance and speed of light and a bunch of other things kind of go against you. And barring new technologies, which are actually not impossible to envision, there's some carbon nanotube stuff and some interesting technologies out there that might take us forward, but certainly in the near future, we're stuck. Okay, and the best we can do is not try to make an individual processor faster, but rather put a bunch of them together and force you guys to figure out how to use them together in a way that gets you faster performance. Okay, this is the Intels and the AMDs and everybody in the world saying, well, I can't do it anymore. We'll give you more processors. You guys figure it out. Yeah, question?
Why is that better from a power perspective? The grade curve keeps going up.
Why is it better from a power perspective? Well, the bottom line is by not trying to be as aggressive with a single processor, a lot of the aggressiveness we've been talking about, out-of-order execution, speculation, that burns power. To try to discover parallelism from something the programmer sort of made opaque for you. By not doing all that and going back to simpler pipelines and putting a bunch of them together, we get a big power advantage right there, assuming the programmer can figure it out.
Would you say it's largely a function of reduction in control complexity then?
I would say it's a reduction in control complexity, but also the fact that we're not guessing anymore, right? The programmer's telling you exactly what the parallelism is. There's several things like that. And the argument you're bringing up, by the way, why should it be better to put more things down? You can only say what I did so often, and at some point there's a limit where, yeah, I put more things down and I got power problems again. And so people who get into the esoteric arguments of, well, you'll never have more than 16 processors on a mainstream chip are arguing about the power limits on the other side. Okay, good question. Any other questions? Is it true that most of the power goes into the processing, not communication? I would say that's not true. Depending on how you look at things, the network, well, again, you can only look at real artifacts. There's been a lot of guessing. People guessed that when you put a bunch of processors together on the chip, in fact, the network communicating between them was going to be more power than the processors by a huge amount. Like, oh, the network will be 90% and the processor's 10. Now, it turns out that was an overestimate, and now we're kind of more in the network is about 30%, the processors maybe another 30, some of the memory I/O maybe another 30. Okay, so but usually that's because the person designing the chip is trying to balance it that way. But yeah, so I would say no, it's not just the processor, it's all the interconnection as well, and the memory. In fact, memory is probably one of the biggest power hogs right now if you look at a server. Okay. All right, any other questions? So what do we do? Well, we could give up, but that would be bad if you're trying to make money selling processors. So let me just give you some ways of relaxing the sequential model. Remember, what got us in this mess was really the fact that we wanted to hide from the programmer the fact that we were expressing parallelism underneath to the transistors. So if we give up on making it completely transparent to the programmer, there's lots of things you can do. Now this one, VLIW, very long instruction word, is still an attempt to hide it from the programmer, but not the compiler. Okay, and so the idea here is very simply, well, rather than an instruction expressing only one thing at a time, we allow it to express a couple of integer ops, let's say a couple of memory operations and some floating point ops, where the compiler or programmer in worst case scenario has told the machine that these things do not depend on each other. It will not be the case that the floating point operation of an add that I put here depends on the multiply op I put here. Okay, so the compiler has explicitly told the hardware, don't worry about it. And notice how we've just thrown out a whole bunch of complexity. Okay, control complexity. So each instruction has an explicit coding here. It's kind of interesting. There have been many different terminologies for in Itanium, which is one of the Intel VLIW type things. Each one of these is called, the grouping is called a packet. In Transmeta, grouping was called a molecule with atoms in it and so on. You can imagine the terms come out. But each operation is a fixed function. These take constant latency, so these are things the compiler can figure out. And the architecture will give you the wrong answer unless the compiler guarantees that you never put two things that depend on each other in the wrong places at the wrong time. So notice how this is a case where a buggy compiler can give you the wrong answer. Of course, that's a big surprise, right? And you need very special compiler support for this. Now, VLIW type machines are in a lot of places. They didn't hit quite the mainstream that everybody expected, but they actually show up in a lot of embedded apps these days, embedded processors. And they even showed up in the Transmeta processor, which was an x86 clone. So let's just show you, just briefly, so you can understand what this might be like. Here's a loop where we're going to go through an array, and we're going to add something to every element of the array. So we do a load, we do an add, we do a store, we increment our index, we loop. Okay? That seems simple, hopefully, to everybody. And if you look here, what could we do in a VLIW? Well, we could have many iterations unrolled simultaneously such that we do two loads here, two loads here, two loads here. This load is feeding that add, so that's one iteration, right? And that add feeds that store. So one iteration is here, but you can see several of them are overlapped simultaneously. Does everybody kind of catch me there? And so here we've unrolled 7 at a time. It results in about 9 clock cycles total, or 1.3 clocks per iteration, which is about a 1.8x speed up over, say, a scalar version of this. Okay? And of course, you see a lot of waste here. Right? And one of the big problems with VLIW was you wasted space. And so here is the same thing, software pipelined. I'll leave you guys to look at this out and figure this out later. But I can actually jam things in a way such that you load on one iteration, you go all the way around, you do the add, you go all the way around, you do the store, and this has actually got 9 iterations simultaneously overlapped here in a software pipeline fashion. Woohoo! And it gets very high utilization. In fact, we could have one less floating point unit and do the same loop. Okay. If you were in one of my classes, we'd actually go through this, but I'll leave it to the readers to take a look earlier, or to look at this later. Okay. Any questions on BLIW? So notice that we've basically relaxed our serial constraint. We said, okay, well, somebody's going to have to worry about parallelism. What about vector? Okay. Now, it turns out there's a lot of stuff that we care about on a day-to-day basis that's actually expressible well as vectors. So it turns out a lot of the graphics type things that you might, applications that you might use, a lot of the physical simulation you might have in a game. So, you know, you're playing a game and the bullets are flying around. That's all done, I mean, it's sort of expressible as vectors. And here's the idea here. We've got a loop. And notice that if we were to unroll this, or take this loop and put it in serial form, we've got a bunch of index loads. We've got to load values. We've got to do some adds and stores. This looks like pretty complicated. Here's the vector code. Set the vector length to 64. Load A. Load B. Do the add of the vector. Store back. You're done. Okay, now isn't that nice? Right? It basically says, I accept that these are vectors, and therefore I'm going to let the hardware load them and add them together and store the result back. And voila, now the hardware knows that these are parallel because it knows what a vector load is like. It knows what a vector add is like. It knows that the first element doesn't depend on the second element, and it can optimize that. What's the cost? Well, we've forced, again, the compiler or the programmer to express something different than just this serial loop in C. I would argue, by the way, that this serial loop in C is not necessarily the right way to express this. You'd like to have some language like MATLAB or something that lets you express vectors as sums and products of things and be done with it. Much easier for the programmer. You know, why do you have to come up with this index I, which is kind of an artificial thing? Okay. Okay, so this is another example of letting the hardware, telling the hardware about parallelism so it can exploit it without all of that control overhead of figuring out what can run in parallel and what can't. So, you know, for a typical vector programming model, you've got these vector registers, which are long arrays of elements, and then some scalar registers. You probably have arithmetic operations like a vector add, which takes, you know, here's the first 2 elements, adds them to get the first element of the result, and so on. You have vector load instructions that say load from memory into a vector register, and what I'm showing you here is a strided operation. So we're actually loading, starting at some point in memory, and each element that goes into the register is gotten by taking the base address and adding an offset to it. Can anybody tell me, by the way, why having a stride is useful in a vector? Yeah, you got a matrix. It's stored in memory in one form and you want to get the other form. So it was stored in row major and you want to get the column out, or vice versa. Stride is great for that. Okay? So, of course, you can overlap multiple vector instructions if they're not related to each other. So here we go back again, right? So here's a load feeding into a multiply, feeding into an add, and notice how this is a 32-element vector. I'm grabbing 8 at a time because the hardware can. It could grab 32 at a time if it wanted. That load is feeding into a multiply, and so after the cycle where all 8 of these are loaded, I can feed them to the multiply unit, and after the first 8 of these are done, I can feed them into the adder, and now the vector unit can be pipelined in any way it wants. This is called chaining. Okay, done by vector supercomputers since Cray. And we can even talk about executing vectors out of order if we wanted to. Okay, now most people don't go that far, but okay, it's all about making sure that you end up producing what it is the programmer thinks they asked you to do. That's the most important part. Okay. Now the last thing that I want to mention is SIMD here, which is single instruction multiple data. And the idea, this is actually a dual of vector architectures if you look at it the right way. But in fact, what you see here is you've got a single instruction fetch unit and a bunch of parallel data units, and the instruction is being fed to every data unit simultaneously, saying, okay, you do your add now, and you do your add, you do your add, and each of these units are working on a different piece of data. Okay, single instruction, multiple data. Can everybody see the dual to vector there, kind of, right? I mean, it's like there's a vector, the vector is distributed across the processor elements here. Okay? Several architectures were actually built exactly like this 20 years ago. Okay? And, certain types of data operations work really well here. You have all probably heard of the pseudo SIMD, which is the poor man's version that's been on Intel and x86 processors for a long time, where what you do is you actually take something like, let's say, a 32-bit word, and you say, well, treat it as if it were a vector of 4 elements. Okay, and you could imagine 32 bits could be 4 8-bit elements, right? And then I could imagine that when I add these guys together, it's like a vector on 4 elements, except that what I have to do, for those of you that are busy thinking, is I have to break the carry chain so that basically these two add to here, these two add to here, and there's no sort of crosstalk between the bins. Okay, so you can easily take a 32-bit adder and turn it into a 4-entry SIMD vector, and I put that in quotes, processor. Okay, and this is available, has been on x86 boxes for 15 years. There have been various iterations, SSE, SSE2, and so on. Sometimes the longer ones actually have 64 bits at a time. Okay? All right, good. Any questions on this? Notice what I've done here. Oh, go ahead, yeah. How long can the vectors be in hardware? Well, this is completely dependent on the hardware, and you can get vectors 128. I've seen 1024. Depends on how big the supercomputer is. The neat thing about vectors, if you think about it, and it's kind of shown by this diagram, is I can build hardware that, say, deals with 32 entry vectors but only does them 8 at a time, or I can build hardware that does the 32 vectors 32 at a time. Right? And I could have those two pieces of hardware, and in theory, the same code could run on each, just one runs faster. So the waste starts coming in the startup time and a few other things. So you can imagine I'm showing you instantaneous fetch and start here, but there's usually a startup time and a shutdown time. And so if you make this all 32 at a time, then the overhead might get in the way. And so it depends a lot on your architecture. And it also, it's more power, and so you might want to build a lower end, less powerful version that still gets a lot of parallelism. And this, by the way, this 8-way parallelism, so why am I saying 8-way? Well, because I'm doing 8 parallel things at a time here. This 8-way parallelism is already much higher than you normally get from one of those super duper out of order superscalar processors I mentioned earlier. So if you were to do the same loop and put it in a superscalar processor, you're not going to get a nice, clean 8 things at a time. So this guy is already way better for this type of application, I got to say, qualify that, than the out of order was. Okay. By the way, these trade-offs are things that architects worry about all the time. Well, there's power. What's my application space look like? If I can't use 32-word vectors very often, then it doesn't make any sense to design them, and so on. Okay, good question. So what we're going to do is one more thing before we break, and that is, let's relax the sequential model further. So notice what I've been doing is I've been pushing around the edges. I've been saying, well, originally it's all serial and the programmer doesn't have to think any differently. And then I said, well, VLIW, now the compiler / programmer has to think differently. Vector, SIMD, probably more so. Problem is you can only do so much of that. Fortunately, by the way, vectors you can do a lot of, because things people care about today are graphics and all sorts of cool things like that. But what if we want to go even further? And that would be where we start thinking about threading. Okay, now thread level parallelism is different from instruction level parallelism in that instruction level parallelism kind of says, I'm going to look at all the implicit parallelism in an instruction stream that the programmer didn't tell me about. But I'll find it. Thread level parallelism is parallelism the programmer tells you about. These two instruction streams can run at the same time or concurrently, depending on what your hardware is. Okay, those are not quite the same thing. In fact, I want to say a little bit about this. So concurrency is when two tasks could start, run, and complete in overlapping time periods. So you got two threads. What the programmer has said is, yeah, these could run independent of each other. There's no guarantee that the hardware or operating system will actually run them in parallel. Okay, but you got to think as if they were. Parallelism, which is kind of what this short course is about, is when the threads or whatever are actually running in parallel. Okay, so what we're going to start with now is we're going to talk about thread models which might or might not run in parallel, but will certainly be concurrent. Okay, is everybody with me on that? And then when we get to concurrent hardware, namely multi-core, then they will really be running in parallel. So our goal here is going to be, in the short term, to use multiple instruction streams to improve the throughput of computers that run many programs, or maybe the instruction time of multi-threaded type programs, etc. But let's understand what a thread is first. So what is a thread? Well, a thread is an independent instruction stream worth of work. And there's several ways of creating them. So for instance, if you have some language with this idea, co-begin, co-end, you might say, here's a set of jobs, and what will happen is all of these will be forked off independently. So job 1 will run in a separate thread from job 2. Okay? Fork join parallelism might look like this, where what we say is, I'm running a parent, I fork off job 1, which is now going to go off and run on its own somewhere, and the parent continues to run job 2. So this fork parallelism forked off a child process, and we now have 2 because we have the parent. Okay, notice how this is a little less clean than this, but it's more general. You can do more types of parallelism with fork join parallelism. And then this notion of join, by the way, is I'm going to wait here until the original thread that I forked off here is done. And so after I exit the join, I know both the child and the parent have completed, and I go forward. Okay? Now that's the simplest type of synchronization so far, and we're going to talk about synchronization a little bit later too. Here's one of another type of parallelism which I kind of like, which is implicit parallelism in the following sense. I say future, wrap it around, or wrap some job around the word future, or wrap future around the job, excuse me, and get back something which is like a result. So the way to read this is that V is the result of running job 1. What did I get with a future? What I said was, well, you go ahead and maybe run it in parallel if you can find the extra processor to do it. So this particular language, or this particular form of the language, doesn't really tell me that I get another thread, but it says that if it's needed for parallelism's sake, it'll go get me another thread. And what happens is if this is off running somewhere else, this is running in Russia, and I go to actually use V, there's an implicit synchronization there that, oh, V's not ready yet, I'll stall you. And then when the job finishes, you get V back. And so the person using V here doesn't have to care about whether this got turned into a thread or not. Okay? So threads may or may not turn into actual computations, but if they don't, then you need to have some semantics where you won't lose them, won't lose the semantics if they do or don't. Okay. So POSIX stands for Portable Operating Systems Interface for Unix, and this is the first sort of threading interface you're going to see over the course of these 3 days. And I'm giving this because it's sort of the lowest level threading interface, and it'll help us illustrate some ideas. Pthreads is the POSIX threading interface. Okay, and it's actually, there's a standard, IEEE standard 1003.1c that's got the POSIX thread interface in it. And it's basically a set of interfaces that let you create parallelism in the form of threads, let you synchronize threads. There's no explicit support for communication in this language because it's assumed that you have shared memory. So the way that you have two threads talk to each other is you allocate something on the heap and then pass pointers to them and they communicate through the heap. Okay, so Pthreads is explicitly a shared memory communication style. Here's an example. So pthread create is the most primitive thing here. It's got some arguments, and the idea is it creates a thread. What are these arguments? Well, one of them is a thread structure, which will let you control that thread later. There's some attributes. More interestingly here is the actual function. So this is the function you want to have run, and here are its arguments. Okay, and for those of you that care about such things, these are all void stars and so on. So they're kind of completely unspecified. Okay, and what comes back is an error code, which is 0 unless you got a problem. Okay. Now, by the way, just Google Pthreads and you'll find complete interfaces. There's plenty of sites up there to give you the details of this. But here's an example. Here's some routine. Say hello. This is like that Lionel Richie song, which none of you remember because you're too young. But so hello world. Basically pretty simple. Notice what we do is we make 16 thread structures. We go through and say pthread create for each of those thread structures, and now we've got 16 parallel threads that are all going to say hello world. And then notice that after we're done with this creation process, there are 16 threads, but the parent is still running. Okay, so there's really 17 threads. And so the 17th one, the parent, goes through and says join, 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 which effectively says wait for thread 0, thread 1, thread 2, thread 3, thread 15. And when we finally exit this loop, we know that all of the 16 child threads are done and we can finish. Okay, so this is the simplest and some would argue probably lowest level thread interface that you'd ever run into. What a lot of the course is for the rest of the few days is how to be much higher level than this. Okay, because if you're busy creating individual threads, it's very hard to get the right number of threads to get them communicating in the right way, to distribute them, and so on. So you're probably not going to be forced to do this. Although in your programming exercise, you will have an option to do threading. You will do threading, and one of the options would be to use Pthreads. I think there's another one to use OpenMP, which you'll learn much more about in a later lecture. Okay? So variables declared outside a main are shared in this kind of thing. Objects allocated on the heap may be shared. Variables on the stack are not. Okay, so if you have local variables inside of your threads, they're not going to communicate. Okay, and here's an example where I create this string called hello world, and then I can pass that as an argument to all of my functions, and they can dereference that pointer. Okay, so typically the argument of a pthread is pthread create is some data structure with a lot of data in it. Okay. So now what can we do with this? Well, we could build loop level parallelism. Like suppose we have some linear algebra thing where every iteration of this loop is independent. We could fork a thread for every iteration. Okay? Is this a good idea or not? How many people think this is a good idea? I'm asking too many leading questions. How many think this might be a bad idea? Okay, why might this be a bad idea? Yeah, there's some overhead to create the threads. Suppose I've only got one processor. Remember, we haven't gotten to parallel processors yet. Suppose I've only got one processor and I create 1,000 threads. I probably grind that thing to a halt via overhead. So you got to be very careful how much parallelism you create. It's got to be an appropriate amount. Okay, and now, of course, those of you who haven't done parallel programming are starting to worry about what's an appropriate amount. And again, that's what we're teaching you, right? But so the overhead of thread creation is non-trivial. You got to be careful. So in this case, whatever this update stuff is, it better not be adding two numbers together, or you got a problem. And a common performance pitfall is too many threads. So let's talk now. Okay, so that was introduction to a little bit of what a threading interface might look like. But so what is multi-threaded execution? Well, this is a situation where you got a bunch of threads, and now the trick is how do they execute? Okay, and every operating system since, well, Multics and earlier actually, has been able to give you the illusion that threads are executing at the same time, right? And what does it do? It does this by multiplexing. You run a little bit of thread 1, then a little bit of thread 2, and then a little bit of thread 3. Okay? We can actually ask the hardware to multitask for us. Okay? How many of you have a computer that's got hyper-threading on it? Or how many of you know that you have a computer that has hyper-threading on it? Okay? I'm going to tell you what hyper-threading is in just a moment. Suffice it to say that it's hardware support that allows you to have more than one thread multiplexed, but the hardware is doing the multiplexing, not the operating system. Okay? So we can actually have the hardware do switching, and we can imagine that that's much faster than the operating system because it's in the hardware. We can imagine that the hardware switches every instruction, or maybe it runs blocks of instructions, right? Who knows? That depends on the hardware. I'll tell you this, the operating system never switches every instruction. Why is that? Way too much overhead. Okay, the hardware, it's a different story. When do you switch between threads? Okay, again, this is a question for the hardware. Could be fine grain, could be coarse grain. What about this? We got threads that we've created. We've created thread A, B, C, D, E. Here's time roughly here, so I guess A creates C creates E, and then B creates D. What order do the threads run in? Do they run A, B, C, D, E? Don't know, right? Okay. Problem is, it's up to the operating system or the hardware what order they run in. Better keep that in mind. If you ever write a parallel program that depends, for instance, on A finishing before B starts, you got a problem. Because there's no guarantee that that's going to happen without synchronization. Okay? So, and worse is it may be that ideally you have A run, then C, then E, or A, C, E alternate, and then B and D alternate. How do you do that? Okay, now, this is where you start getting into the tuning of performance. So some operating systems, Linux and so on these days, give you the ability to give hints of when to run things. Or what's the affinity? These two threads should run on one processor and these two should run on another. Okay, but you need to be looking for those options. In the ParLab, we're actually busy designing new operating systems so that we can give the programmer explicit control over user-level scheduling. So they can decide exactly how things are scheduled. Okay, but I want you to keep scheduling in mind. It's a question. Okay? All right. Any questions on that? Now, okay, go ahead. So what is the overhead of shared memory is a great question here, and that's completely dependent on the hardware. Now, so far, since we haven't actually gotten to multiprocessors quite yet, the shared memory cost here is supposedly relatively low because underneath it's all the same memory system. For starters. Once we've got many processors, now the question is, what does it cost to write in one processor and read from the other one? Depends on the hardware. Sometimes it's fast, sometimes it's not. If you've got 1,000 processors, it's not going to be as fast as you think. Okay? So, yeah, back in the 90s, there were lots of parallel programming projects, because as you all remember, I told you parallelism is not new, right? And there were actual PhDs of students that were gotten by taking a single application and parallelizing on a particular shared memory architecture to get the best performance. Got a whole PhD out of that. Okay, and there's a lot of them. So, and I don't want to minimize the work they did because there was a lot of it. Okay, so getting good performance out of shared memory is hard. I just thought I'd toss that in there. So let's finish up this little thought and get you to a break with the following. So what about combining instruction level parallelism and thread level parallelism? All right? Well, there are different types of parallelism, right? Thread level parallelism, the programmer explicitly puts something out in a somewhat coarser grained mode. Instruction level parallelism, the hardware is busy discovering parallel instructions that can run together in parallel, okay? And so you might ask yourself, if a processor oriented at instruction level parallelism could benefit from thread level parallelism. Okay, and why might we even think this, right? One is the functional units are often idle in the data paths designed for ILP. Remember, we had the little tiny bit of black at the bottom of that diagram. I'll show you again so you remember. Maybe if we could make things busier, that might be the benefit of putting threads in. Okay, TLP is good because the programmer has already said this stuff is parallel. You don't have to figure out whether it's parallel, right? These two threads don't depend on each other except for synchronization. So this is actually called simultaneous multi-threading, and Intel, which never, as with a lot of companies, never likes to use a word that somebody else has published, calls this hyperthreading. Okay? So remind you, remember this diagram? See this black down at the bottom that's kind of missing? This is the only thing that's useful. Okay, wouldn't it be nice if we could fill out these slots up here with other threads? And the idea here of simultaneous multithreading is very simple. So what you see here is cycle 1, 2, 3, 4, 5. These are all the parallel operations that could be done in parallel in an out-of-order execution unit. And notice the yellow here are units, or slots that are actually being used by the yellow thread. So this, on cycle 1, this yellow thread manages to get this multiplier and this condition code unit working. It manages to get 2 multipliers and a branch unit working here, and so on. Okay, and notice all the white space. And this white space comes because of hazards, branch mispredictions, all that stuff I mentioned. Okay, and this is why we waste a lot of power doing this. If you look here, if I put 2 threads together, there's a potential of actually filling more slots. Okay, so the yellow thread and the blue thread are both sharing the same pipeline, and as a result, we have less wasted time in the pipeline. Okay, so that's hyperthreading, or simultaneous multithreading is the real word for it. Okay? Questions on this? So here's a case, by the way, where what we've done is we made the programmer come up with the threads. We've thrown it at the hardware. The hardware comes up with more parallelism within threads, and we get both ILP and TLP simultaneously. Of course, any of you who have really pushed this hard realize that the potential for parallelism is not a factor of 2 here. It's 30% or something. Okay. Here's an actual power 5. By the way, I showed you the power 4 earlier. The only difference between the power 4 and the power 5, other than an increment in the number of the name of the chip, is they actually put in simultaneous multi-threading with 2 threads, and it turns out that you can do this with just a little bit of extra stuff. So you've got a couple of extra instruction buffers, a couple of extra branch prediction sort of structures, some extra program counters and registers, and most of the pipeline is the same, which is kind of cool. And so the Power 5 core ended up being about 24% larger than the Power 4 core, and it gave you the 2 threads. Okay? Good. So questions, and then we'll break. Any other questions? Okay, so that clock there is a little bit off, but let's take about 15-minute break here and get back about 1:45. Okay? Give you guys a chance to walk around a little bit, and we'll switch gears a little bit. I'll be up here for questions if anybody wants to ask questions in the break too.
Extensively, I teach at UC Davis.
Oh, great.
So I was the one who asked the question about sort of why do you go to multiple cores and why is that better from a power perspective? I get this question a lot. And,
Yeah.
I didn't want to get in a big argument in class, but if we look at like a Core i7, you know, it's got an order execution and it's got hyperthreading and it's you know, and you said, well, it's largely the control complexity that makes it less complicated. But I would say those are fairly complicated.
So Intel is in a different market. So Intel is in the market where they don't want to lose the single thread performance of chips to whatever extent. And so think of them as they run against this barrier. They're not going to make individual things better, so they can put more of it down. If they really wanted to go, and they're getting the performance improvement, or the power improvement, because the technology continues to get smaller. So they get a little technology improvement on the power standpoint, and they put more down rather than trying to make every individual one better.
I mean, one argument I usually make is like, well, you sort of have this curve between things get better and power gets more, and it sort of levels off. And so it's like, well, just stopping on that curve probably helps. And then I do a big electrical argument about like capacitance and scaling and so on.
Sure.
But
yeah, I didn't want to get into a lot of detail, but
I'm interested in this take because it's kind of a subtle argument to make.
I think the problem is parallelism isn't really ready to be mainstream. Okay? And therefore, So the question is, what does Intel do? Well, they can't make their individual processors ride any curve like they used to. So they got to hope that things are, from the parallel principle, they got to hope that things get better. And so what they do is, to the extent that they can continue improving the i7 or whatever, they're going to make it. They're not going to make it more complicated, but they'll try to improve the power efficiency. They'll do clock gating. They'll do all that stuff. But they still have to have something they can claim has gotten radically different or better. What do? You put more of them.
More is better.
More is better. Hopefully somebody will figure out how to use more.
Okay.
More is better. The power of an individual one has probably gone down a little bit. The performance is kind of oscillating about the same. It's not improving a lot, right? We're putting more, therefore we've doubled the number of cores, so our performance in the grand scheme is faster by a factor of 2 or something, some argument like that.
And they're able to build libraries and so on that actually use
yes,
that
exactly.
Might actually be interesting.
So I would say that's kind of where they're at. Now, if you weren't trying to be backward compatible with a wide array of stuff, then you probably wouldn't make those decisions. You rip out a lot of that crap and you go down to simple two-way superscalar something.
As they did in Laravel.
Right. Although, unfortunately, they weren't able to compete with their
I'm a little more on the graphics side. I'm familiar with that story, although we're going to see it again.
Yeah, I'm sure.
Corner is,
But so I would say that, you know, the extended answer to your argument is it's really a balance between market and power efficiency. And the ultimate power efficiency argument probably isn't going to fly with somebody trying to stay backward compatible on the market like an Intel. But if you didn't have to worry about that, I would say probably the simpler processors, mostly simpler processors, with a few of the really big ones for the serial code
okay.
sections.
So you would actually make it heterogeneous.
Yes.
Okay.
And I think that's probably the most flexible power efficient architecture that you can
I totally agree with that. I mean, there's a lot of other problems that I know you and I are both thinking about to make that work. But anyway, it's very nice to see this take. This is
sorry if this ends. I'm trying to cover lots of sort of background material.
I've got slides from so many places, and your slides are closer to my lecture style than anybody else I've borrowed from. So it's really nice.
Great.
I just have a question about the purpose of the thread priority. So
the purpose of what?
So the thread priority is on the side.
Right.
Who controls that?
So that's actually, let's see, depends on the architecture. I think on the Power 5, that's actually something you can set.
Okay. So
The operating system can choose thread priorities, and if you look at the, they actually show performance of the individual, the two threads, as you put them together, as a function of changing the thread priorities relative to each other, 1 to 7 or whatever. And what you actually see is you can make them both the same priority, and that gives you kind of better performance than a single one. But each thread is running slower than it was before. And then you can tweak it up so that one thread is highest priority and the other one just sort of comes in when the thread is idle. And there you get pretty close to the high priority thread gets the original thing it was, and the other one gets a little bit and it adds something to the performance. But anyway, that's tweakable.
okay, so that is an operating system.
From what I remember, it is.
Yeah.
I think so. And I think it varies from 0 to 7 or 1 to 7 or something. Hey. Hi.
Yeah, it's fun listening to you again. Because like I was like listening to a lecture on these podcasts that we posted 4 years ago back
Oh, I
home
see.
to my undergrad,
Sure.
back home girls like Palestine. But anyway, I have a question about you mentioned about projects having users controlling the order of things and the operating system level. So what advantage of that? Because like this also things going quickly and it is on the or someone
Well,
else deal about it, not the user deal.
Well, so the user is a funny word there. It's user level. Okay, so you could imagine you've got an application that has some behavior based on whatever programming model it was and what its properties are. So you could have something with hierarchical parallelism that uses thread stealing. That's kind of one style. Another might be loops, like I showed you, where you fork off a bunch of loops. Those are very different schedulers that they want.
The user like it's not actually controlling which thread, but controlling the scheduling mechanism.
Well, controlling if you have two threads that need to run, that could run, which one do you choose? That kind of decision, which the operating system does, you could do at user level. And the trick is to make that, and there are operating systems that do that already. But we're making it much easier to do and with higher performance. To have, in principle, every thread's got a user level scheduler. Or not every thread, but every process.
That's not the distillation.
Yeah.
So the other question is like, have you considered like raising the abstraction level in the hardware by applying techniques from service-oriented architecture?
From what?
By applying techniques from service-oriented architecture, like looking at the hardware as services, service provider.
Sure. Yeah. Actually, so tessellation has this kind of view of quality of service, which we could talk more about later if you like. No, it's okay. No, it's a longer discussion than we have time.
Yeah, but I'm arguing like, did you have go beyond the operating system to the hardware?
Yeah. So ideally, to do that well, you put hardware in. It gives you the ability to actually do performance isolation and get quality of service out of it. So we're actually looking at some hardware mechanisms to enhance the ability of the operating system to provide that sort of property. It's not required, but then you don't get as good a behavior as if you had it.
Yeah, you need some support from
Exactly. Yep. Great. Question? Hi. Hi.
And recently, I have been wrong that we use many cars. But how about the risk of the process level failure? Process level failure, when we, for example, we set up an impact benchmark and it runs, and then a car crashed, and then our work crashed. So how about the failure on our modern supercomputers?
So in particular, so which things are you worried about? So you're worried about reliability, or so that it doesn't crash too often, or what?
I think that it will happen usually when we run the benchmark.
That it crashed a lot?
Yeah.
Yeah, the problem with parallelism, it's easy to end up with something that's not very reliable too. There's a lot of work involved in that. So there will be some discussion of debugging and correctness in later parts of the course.
How about the frequency of the failure happen in the supercomputer used in
Yeah, I think it depends on what applications you're running, because different applications fail more frequently than others.
for example, the impact. How does that failure?
I don't know Linpack as well as Jim Demmel, who was the person who started before me. So you should ask him that question tomorrow morning. Okay?
That's going to be great.
Yeah.
Thank you.
Sure. Okay. We'll give people another couple minutes. All right. Let's start up again. So before we pile in to parallelism, you realize that we've been kind of working on the edges of parallelism. I want to bring up one last thing here, which is a big issue. So the big issue I want to talk about briefly is the memory system. And let me show you a graph here to tell you a little bit about memory. So back in the heyday before 2002, when CPUs were growing rapidly in performance at roughly 60% per year, 2x every 1.5 years, DRAM was not getting faster by the same amount. Okay, now remember, once again, like every other graph I'll probably show you today, this is a log linear scale. And so these two different slopes represent two different exponential constants. All right, so what that says is the speed of the processors were growing away from the speed of DRAM exponentially fast. For those that use terminology poorly, people like to call this Moore's law, which is really Joy's law, right? I like to call this one Less's law. Sorry, it's a bad computer architecture joke. But so the question is, how does an architect cope with this gap? Because if you can't feed your processor as fast as it needs, then basically you've made a really fast processor that spends all its time stalling on memory. So, of course, what's the principle that people use? Called locality. If it turned out that applications didn't have a lot of locality to them, computer architecture would not have gotten as far as it did. Now, there's two different types of locality, which we go into great detail in computer architecture classes, temporal and spatial. Temporal locality basically says if you use something, you're likely to use it again soon. Spatial locality says that if you use something, you're likely to use something close to it or related to it soon. Okay, these are close to each other. I mean, they're similar, but not quite the same thing. And the last 25, 30 years, whatever, hardware has really required locality to get any speed. And that's because the DRAM has been getting exponentially slow relative to the processor. And that's been a problem. Okay, so how do we fix this? Caching. Assuming that we have some sort of locality, we're going to put stuff that we use recently in a cache and hope that that's enough to get us our performance back. Okay? Now, let me show you something here. So here is just to give our, to calibrate everybody, here's a graph where we have time along the bottom axis. This is actually an address up here. And so what you see here is you see a dot for every address that's accessed at a given time, right? So if you take a time slice through here, you see all the addresses being accessed at that time. Now, what you see here is temporal locality. See how we keep using the same thing over and over and over again? Here you see spatial locality, where when we use something, we're likely to use things that are close to it in its address space. For those of you that are programmers, let me just give you a little bit of a way to think about spatial locality. Imagine a structure, right? You make a structure for points that has x, y, and z in it. That data structure is probably stored in adjacent addresses, and therefore when you use x, you're likely to use y, likely to use z. That's spatial locality. Okay? Here is bad locality. Excuse me. See how we're walking our way through a set of addresses? All right? So, it turns out that caching for temporal locality is easy. You just store the data in some location. Spatial locality is pretty easy. You just grab a chunk of things when you grab one. Bad locality is hard to deal with. How do you deal with bad locality in a cache? Prefetching. Assuming that I can recognize that I'm walking my way through this pattern, then maybe the hardware can figure that out and prefetch it so that it's ready when I need it. Okay? Other ways to deal with it is you don't bother caching at all, and you use a vector load or store where the vectors are not going through the cache at all, but they have the pattern of loads. They tell the memory system, I'm going to load like this. It's kind of like better than prefetching because the programmer, through his load pattern, has told the memory exactly what he wants. All right? So there are ways around bad locality, but it turns out that there's a lot of good locality we can deal with. And so we build a memory hierarchy to do that. Here's an example of a memory hierarchy where we have a processor, we have some registers, which you could think of as the ultimate high-speed cache, right? You only put things in registers you're using in the next few instructions. You put things in the on-chip caches, which may have multiple levels for things that have good spatial or temporal locality, and then you might have second and third level caches. You might have main memory and DRAM, and then, of course, with paging, you could actually think of the disk as a cache on the memory, and you could think of tape, which nobody knows what a tape is anymore, as a cache on the disk. So the goal of this kind of structure is you want the speed of the smallest thing with the size of the biggest thing, right? You want to fake it out. So it looks like it's got the speed of the smallest thing. Oops, sorry. Looks like it's got the speed of the smallest thing and the size of the biggest thing. And of course, that only works well if you've got enough locality to hide it. All right. Now here is a very recent chip. And if you look carefully at this chip, what you see here is here's a bunch of cores. Here is a third level cache on chip. All right, so level 3 cache on chip is common today. Okay, this is unheard of a decade ago. All right, a decade ago you might have had 1 level or 2 on chip. Okay, so people take their principles of locality very seriously in order to get any performance whatsoever. And what's interesting to me is what fraction of the chip would you say is the L3 cache? Well, this looks like it's maybe a third of the chip at least. Okay, so a third of the area is doing nothing but storing data to try to make up for the fact that DRAM is slow. You should let that sink in because that says that, boy, your program better have locality in it or it's not going to perform well at all. And the reason I know that is because these architects spent all this time laying down cache. Of course, the skeptics in the audience would say, well, they don't know what else to do because they can't program more than 4 cores anyway, so they put cache down because they didn't know anything better. Yeah, 6 of one, 6.5 of one, half a baker's dozen of the other on that, I'd say. So, but cache is very important. So terminology, okay, this is, hopefully this is obvious to everybody. What's a hit in the cache? Well, you go to look at the upper level, you find the data you want, that's a hit. Okay, we can talk about the hit rate. What fraction of the time do I look in the cache and I find data there? If my hit rate is 50% or 20%, I'm getting no locality and I'm seeing the full latency of the DRAM, and it's probably bad. If my hit rate's 99%, I'm doing well. Okay, what's a miss? Right, a miss is you go to look, it's not a hit. Right, so the miss rate is 1 minus the hit rate. And an important thing we can talk about is the miss penalty, which is a very interesting architectural idea, which is if I miss in the cache, what's the penalty? How long does it actually take to fetch the data and put it back in the cache? And a good, let me just throw some numbers out. It might be the case that in the miss penalty could easily be 600 or 1,000 instructions worth of time to get data out of the DRAM in a penalty. Okay? That's a lot. Now remember, we're talking about processors that are fetching more than one instruction at a time and stuffing things down pipelines and all that sort of stuff. So you could get 500 to 1,000 instructions of missed opportunity when you cache miss, leading to some people to even speculate that there may be situations where rather than bothering to go to the DRAM, why not just recompute the thing? I'm not sure I'd go that far. But so caches are important. Hopefully the hit time is very much less than the miss penalty. All right? Because if the hit time's not very much less than the miss penalty, then there's really no point in going to all the trouble of putting stuff in your cache. So let me just show you a couple of things. I want to make sure we understand how important the cache is. So here's some old data which already showed the issue. So this is the fact that the CPU time has a function of not just how many operations, but how many cache misses. So for instance, let's look at something really simple like sorting. So we have two algorithms, quicksort and radix sort. And you could imagine, this is from a paper which you guys can look up if you want, and you could imagine that if you do an analysis of these two algorithms and you say, suppose that I have this many keys that I'm sorting, and I'm interested in the number of instructions per key. Okay, so as I get more keys, obviously the multiplier on this keeps going up by this axis. But what's interesting here is as the number of keys gets larger, if you just look at the instruction count, you find that radix sort becomes more and more efficient. In fact, there's a crossover point where radix is more efficient than quicksort per key. Okay, now the question is it really like that? Well, no. Here is what it's really like if I take real cache misses into account. And notice that in this case, the quicksort always remains the most efficient, and radix sort, although it starts coming down, ends up running into cache miss problems and very rapidly, not very rapidly, stays the worst algorithm. Okay, so what do you learn from this? You learn that you can't really just analyze the number of instructions in a program. You've got to take the whole memory hierarchy into account. Yipes, I showed you a chip with 3 levels of cache. So that means before you even get to the DRAM, there's at least 3 levels of cache involved, and probably prefetchers. Somebody threw out the word prefetcher earlier, right? There's probably prefetchers involved. Let me show you some other data, which is, so by the way, this actually shows why this performance issue is in there. If you look at the number of cache misses, look at how the radix sort cache misses per key goes up and never, quicksort's much more efficient from a cache miss per key standpoint. So here's a micro benchmark that Kathy Yellick and students came up with, which I think is very indicative of the problem. And it's very simple. Imagine you've got a large array. And what I'm going to do is I am going to go over the array over and over again in the following fashion. I'm going to take, let's look at the stride 1 case, which is very simple. What I'm going to do is I'm going to start with the first element, read it, then the second, then the third, then the fourth. I'm going to read to the end, then I'm going to go back and start over again, and I'm going to do it over and over and over and over and over again, so there's no startup effect. Okay? Now, everybody kind of think what happens there. Now, you may not have a lot of knowledge of caches, but I'll tell you this. When you hit this first one, you cache miss, you bring in a chunk of data. Remember your spatial locality, you put that into your cache. The next few of these are very fast because they're close to each other, because they're already in the cache. And then you get another cache miss and so on. Okay? And if you do this over and over again, the overall performance you're going to see per access will have 2 regimes, right? One regime will be when this whole array fits into the cache. Therefore, after the first time through, it's all in the cache, and then just things are fast. The other regime will be it doesn't fit into the cache, and so every time I go through this, everything's always a cache miss. Okay, so there are 2 regimes. It fits in the cache or it doesn't. Now, what's these other strides? Well, here's a case where what I do is I grab the first element, then I go 2 elements down and grab it, and so on. And I only access the red elements, but I do it over and over again. Okay? You could imagine here that I'm going to get slightly less spatial locality because on each miss, I don't get as many items out of it. Because notice how I'm going faster through the data. Okay? And so on. So now you might say, well, this is simplistic. What happens? Well, we might imagine that if everything fits in the cache, we just get some very fast access time per element, which has to do with single level cache time, first cache time. On the other hand, you can imagine that as I vary my stride, what happens is for the unit stride, I'll have a value here which has to do with cache missing, but then getting most of my all of the spatial locality I can. So it's a little slower than the cache hit time, but it's not too bad. And as I increase my stride, at some point I'll get to where every access is a cache miss. Because I cache miss, I pull in a whole cache line, but then I go beyond it, I cache miss again. And then that's going to be the case for basically most of my strides until I hit the point at which there's so few items that I'm accessing, they actually all fit back in the cache again, because the total amount of blue down here is small. Okay? And so depending on whether this is, say, a 2-way set associative cache or a 3-way set associative cache, if I only have 3 elements in this array, it doesn't matter how big the total array is, they'll all fit in there and I'll get fast again. Okay, so I just explained a very simple mental model of how something like this ought to work for 2 different regimes, either the bigger or the smaller. Or excuse me, the smaller than the cache or the bigger than the cache. What do we get? Well, you go measure, right? Remember how I told you about measuring? So here is this benchmark run on the Sun Ultra 2i. And what you see here is for a variety of different array lengths, what we see is, yeah, there's some things that are kind of flat. There's some others that kind of look like we want them to. But then what the heck is this? Okay, now, I know I actually have a couple of real honest-to-goodness computer architects in the audience. You guys can figure it out if you like. This is complicated. This is not at all that simple little plateau thing, right? Here's an even better one. Well, actually, we can identify these things. So here's like the L1 time, here's the L2 time, and here's the memory time. And then you can figure out what's going on in here. But before you do that, let me show you something even better. Dun, dun. Here is the power 3. Wow. Does that look anything like my little plateau diagram from before? This is so complicated that they actually went to the architects. They said, can you explain this to us? And they looked at it, and they looked at it, and they looked at it, and they said, no. Why is this so complicated? Well, because many levels of cache prefetching. There's some prefetcher that's trying to guess what strides you're doing to pull in the right data so it's there when you need it, right? All of that stuff is working together to give you a basically unpredictably complicated profile of what happens to the cache. Now, there's 2 schools of thought on this. One is, that's ridiculous. Why would you ever do that? What's the answer to that question? It's not ridiculous. It basically makes it faster sometimes, and that hopefully that sometimes is enough of a sometimes that for most applications this does pretty well. The problem is if you're a programmer who's trying to tune to this architecture, what the heck do you do? Because you don't know what stride length and how to lay out your data because this thing is busy going against you. And it's doing it for a good reason, right? Architects are not fickle. They're trying to improve the performance of their chip overall. But this really gets you in trouble if you're trying to tune. And so what do we learn from this? So the caches are vast impactors of performance. The actual performance for a simple program can be very complicated. There are some techniques, by the way, you can go in the literature, you can learn about blocking and tiling and so on to turn linear algebra, regular computations into things that fit in your cache well. But even when you do that, some of these weird prefetching issues are going to get in your way. There's some really good papers on blocking and tiling, which we can point you to if you care. So what is my point on this? I think the closing point is this notion called auto-tuning, which you saw Jim in his intro lecture mentioned about. I think that's going to be day 3, where the idea is that for a given algorithm, you don't know what the best blocking, tiling, stride length, any of that stuff is until you actually run it on the architecture. And so the notion behind auto-tuning is you're going to have several ways of doing something, and you're going to run it on the architecture to find out what the best one is, and that's the one you're going to use. Okay, and that's what auto-tuning is about, or that's what tuning is about, and the auto is hopefully to keep the impact on the programmer to be small. Okay? Good. All right, I want to switch gears unless there are any other memory questions. Yes? Oh, no. Are we good? Okay. So, at this point, if we're Intel, we've decided we can't make a processor whose power efficiency and speed grows on the same Moore's law curve as it used to, and so we got to do something else. And what we do is we throw a bunch of processors down, which basically puts us into the regime of explicitly parallel computer architecture. So what is parallel architecture? Well, you could say a parallel computer is a collection of processing elements that cooperate to solve very large problems. And the most important element here that's different, I think, is about the communication. Suddenly, the programmer has multiple things going on, and they need to figure out how to coordinate between them. Communication here includes synchronization. It includes moving data around. Okay? It includes taking the results from point A and bringing them to point B, etc. So what does the programmer think about in this new regime? Well, you know, there's lots of stuff there. There's parallelisms as old as computer architecture. So they might think about models of programming like PRAM or BSP or sequential consistency. They might worry about resource allocation, like how much of an array do I put on each processor. They might worry about what's in hardware versus software. So there might be, gee, does my single processor look like something in particular? Is it a Core Duo high-performance Intel processor, or is it a little tiny 5-stage pipeline of which I got thousands of them? Is it a SIMD processor? Is it a vector processor? These are all questions that, in principle, you as a programmer of a parallel architecture ought to ask yourself to figure out how to get the best performance out of your app for that piece of hardware. Okay, what's the data access and communication mechanisms? Do you do shared memory? Do you do message passing? Now, why am I naming all these things? It's to scare everybody away. No, to tell you that to do the ideal layout of a parallel program, it's on a particular hardware architecture, there's a lot of things you got to think about in principle. And this is why parallel programming has been so hard to catch on. Because to really tune, you got the memory effects, you got what different communication mechanisms there are, and so on. And it just gets very complicated to do the best thing. Now, maybe you don't have to do exactly the best thing. What you'd like is you'd like something where the parallelism, you get to see benefit of parallelism without the huge effort that has traditionally been done, say, up the hill at LBL to do parallel apps. Okay, there are people whose job is to figure out how to get the best performance out of each piece of hardware. And that is not probably where 99% of you are going to fall. What's more interesting in today's world of commodity parallel processing is techniques for getting good performance out of parallel architectures. And that's what this class is about. You're going to try to figure out techniques for getting good performance, probably not the best, most highly tuned thing possible. Okay? What I want to do is I want to make sure you have some idea of where we're at on the types of parallelism we've got here. So we started out talking roughly about superscalar. We talked about simple simultaneous multi-threading, where, by the way, each color or hash mark is a different thread. So here is the case of hyper-threading or simultaneous multi-threading here, where we sort of said, well, although we can do 4 things at once, they may be shared by different threads. If you look over here, multiprocessing is the explicit decision to basically use, to partition your resources into independent execution units. So here I'm showing 2. So rather than allowing 4-way issue multiple threads to go on at once, I basically have smaller, slightly less powerful 2-way issue processors. Okay? So what programming models do we deal with? Well, the programming model is kind of the way the programmer thinks, made up of languages, libraries that create an abstract view of the machine. They might ask themselves, what type of control mechanism do they have for expressing parallelism? I showed you guys Pthreads earlier. That's a very simplistic way of expressing parallelism. When you start worrying about things like what are the orderings between different operations and how do things synchronize, those are also things I got to talk a little bit about. You might ask yourself about your data. What's private? What's shared? How do you communicate? And you might ask about synchronization. How do you guarantee that two threads are completed with what they're doing so you can move on and get the right answer? Okay, these are all things we're going to say a little bit about. And then you have to ask about the cost, because presumably there's some cost model you're going after in order to make decisions. So let's do a very simple programming example here, which is, suppose that we're trying to add up f of some array. So a of I is an array. I'm adding up f of the array. So you can see in principle there is the array A. There's a new array, which is f of A, and then there's the sum. Very simplistic. Okay? And the question might be this. Where is A? Okay? Is it spread on different processors? Is it all in the same processor? What work is each processor going to do? How do we coordinate to end up with the sum being the right answer? Because I'll tell you, if this is what you want to compute, you don't really want something else. Right? That sounds dumb, but I want to say that. You don't want your result that's in parallel to compute something that's sort of like this. You want to get this. There are some interesting issues with floating point and rounding which come into play also, where you can only reorder in certain ways, but that's beyond the scope of this lecture. So let's start with two different types of programming models, which I think roughly cover what's important here. There's the shared memory and the message passing style. Let's start with shared memory, because that was kind of what we said we had in Pthreads. And what is shared memory? So the idea here is each one of these processors down here shares some chunk of memory somewhere in the system and can basically act as if that memory is attached to each processor. And so, for instance, processor N here can store a value that processor 0 reads, and all that's involved is passing a pointer around. So processor N knows what the pointer is. It stores into the pointer. Processor 0 knows what the pointer is. It reads from the pointer, and communication magically happens. Okay, that's the shared memory programming model. Does that seem simple to everybody? Okay, the reason shared memory, I hope so, the reason shared memory is simple, and I say that in serious quotes, is the theory here is that it's so much like what a uniprocessor programming is to everybody that you don't have to think about it. Right? It's just, yeah, there's data that's stored in memory somewhere. Now, unfortunately, that particular viewpoint isn't really true, and I'm going to show you a little bit why that's not true. But so the program's a collection of threads running on different processors. So in addition to being concurrent, these threads are actually running in parallel. Okay, each thread has a set of private variables on a stack or so on. And then the set of shared variables, sorry, talking too fast, that are in shared memory that can be shared by them. So let's go back to our example here. Were there any questions on the model here, by the way? So let's look at our programming example. How might we do this in the shared memory strategy? Well, let's suppose we have a very small number of processors relative to the size of A. What we can do is we can parallel decompose things so that each processor is going to do a chunk of this sum, and then we're going to combine the results when we're done. Seems simple? Where does A have to live? It's out there, right? It's in the ether, in shared memory. That's cool about shared memory. I don't have to actually put it anywhere. All right? So we assign n over p numbers to each of the p processors because they're going to compute that piece. So each processor computes f of A, sums it up into these green pieces, and then at some point we have to combine them together to do the sum. Okay? Now, what's the performance fallacy about A is just in space and we don't have to worry about it? Why did people get PhDs on tuning parallel apps to shared memory programs. So if two people try to access the same shared memory word at the same time, we might have a problem. That's true. What else? Yeah, we might actually have to do cache misses, and if the data is stored far away, it might take, cache miss time might take a long time to get to there, right? So just because we have the abstraction that the data is out there doesn't mean it's performing well. And of course, the other really big issue here is synchronization, because how do I know that the one that finally sums up these little green dots actually gets the final values as opposed to some partial result because the processors are not fully done? Okay? So let me just show you. Here is a two-thread decomposition of this program. Thread 1 says for I equals 0 to n over 2 minus 1, s equals s plus f of a of I, and thread 2 says for I equals n over 2 n minus 1, s equals s plus f of a over I. And yeah, simple, right? Yes?
For some values of I, the computation of f may take an awful lot longer than it takes for other values of I.
Ah, load balance may be a problem, yes. There's actually a more serious, that's a big problem, but there's a more serious problem, yeah. Yes, there's a very big issue, right? So both of these threads are writing into S. Why would anybody expect this to get me the right answer? Well, the reason they'd expect to get the right answer is they weren't thinking carefully, right? S is shared, so this thread's busy updating S, and this thread is busy updating S, and we end up with garbage when we're done. Okay, and this is the biggest, one of the biggest problems with shared memory programming is the race conditions. You know, and this is load balancing issues aside, which is sort of a second level problem as well. But so a race condition or a data race occurs when two processors or two threads access the same variable and one of them is doing a write. You're going to hear a lot about data races, I suspect, tomorrow when they talk about correctness and debugging. All right? This program will not give you the right answer, I can probably say with 99.9% efficiency, or 99.9% assurance. Let's look at a better version. Okay, so here's a better version. So thread 1 computes f of a, puts it in register 0. Thread 2 computes f of a, puts it in another register. Let's take a look briefly at why that previous code actually failed. Notice that what really happens is we do S goes into register 1, we add into register 1, and we store back. And if you notice, there are some interleavings here where we could load S here, update here, store, and what we've effectively done is there's an interleaving where we just lose updates. Right? Okay? And so for this program to work, we should have 34 at the end, but because of this sort of interleaving, we could end up with 34, we could end up with 9, we could end up with 25. Okay? So how do we, so I'm showing you an example here. This guy loads, computes 9, this computes 25. This guy loads 0 because S is 0. This guy loads 0 because S is 0. This guy adds 0 plus 25 to get 25. This guy stores back 25. This guy loads 0, adds the 9, stores back the 9, and when we're done, we ended up with 9. We effectively just lost an update because of a data race. All right, and this, the reason I went through this is because sometimes people don't see how easy it is for this to happen. Oops. Okay. So how do we fix this? So the problem, by the way, is that our only atomic operations here are reads and writes. So this is kind of getting us into this trouble. But can somebody tell me how to fix this code? Say again?
The partial results are separately.
That's right. We could compute all the partial results separately. So we could go through our loop here and compute S1 and go through and compute S2. But then we still have a problem with combining those two at the end, but it's less of a problem. Okay? So for instance, here we go. That's a good answer. I actually asked him to say that. But here what we're doing is we're computing the first half and the second half, and then we add them in. Okay, so this is much better because the only data race is at the very end. Okay, but much better is kind of, I guess, it's like close is good in hand grenades and horseshoes, right? I'm not sure that much better, when it could still give you a buggy result, is good. But it turns out the fix here is a lot easier, which is what? Yeah. Yeah, all we really have to do is put locks around this. And voila, suddenly we actually got a correct execution. Now, what is that lock doing for me? The lock here is making sure that only one thread can enter this critical section at a time. And as a result, basically, since this has exclusively got access to S, then when we load S into a register, we update the register and store S back. That combination sequence can't get interrupted by the other side because of the locks. And what we've effectively done is we've made S equal S plus something into an atomic operation that can't get interleaved with any other atomic operation. So one view of parallel programming in shared memory is you got to figure out what your required atomic operations are so you get the right answer. Was there a question in the back? Yeah.
Why not just update S after the threads have completed?
So the question of updating S after the threads have completed is another possibility, but then you would also want to, you'd have to have the master thread wait for the two of them to finish, get past, I guess you could have two globals, local S1 and local S2, and then that final thread adds them. It's another way to do it. But see now, what's good here is you guys are thinking as solutions. Okay, you need to know there's a problem first, which is good, yeah.
Floating point addition is not associated.
Yes, floating point addition. Floating point is unfortunately not going to give you the right answer for a lot of these decompositions. And I'll leave that to talking with Jim Demmel about that. No, it's true. You should be aware that taking and doing obvious things with floating point doesn't always give you the right answer when you're worried about rounding. But that's beyond the scope of today. Okay, so any other questions on this? So what do you need to know with shared memory? One is it may not be as fast as you think because you don't really know where it is. When it's out there, it's, it may be close to your processor, it may not. It depends on how good your cache works, and I'm going to talk a little bit about that now. The second thing to know is because of shared memory's nature as being an implicit communication mechanism, right? I communicate simply by writing into the shared memory. Suddenly I have a synchronization issue. I can get data races, I may need to add locks, and so on. Okay, and so making correct shared memory code requires a careful thought process here. So let's talk about caching just briefly, because this is talking about architecture. But here is a typical scenario where we've got a bunch of processors, each with their own private cache, and memory is somewhere. And I'm going to show it off of a bus here. And the question is, we really like high performance for the processor, which because of my little discussion of memory earlier says there's got to be a cache, period. Okay, no argument there. But once we have a cache, which is great, it's reducing average latency and so on, suddenly we've got a problem. All right, so this cache looks great until we've got two processors involved with it. Okay, and then we get the cache coherence problem, which you're probably all familiar with. But here we have variable u is in memory with the value 5. We load it into processor 1's cache. We load it into processor 3's cache. Processor 3 updates with a 7. Processor 1 gets what when it reads back? Does it get 7 or does it get 5? Well, if this were a good machine, it probably would get 7. Okay, if this were a buggy machine, it's probably get 5. Okay, this is the cache coherence problem. You got to make sure, because you've got copies of things, that the copies are kept coherent with each other. Okay, so just because shared memory is a simple way to think doesn't mean it's a simple thing to design if you're a hardware architect. Now, what does processor 2 get? Well, that's another question, because I don't know if this 7 goes all the way to memory, so processor 2 gets the 7, or does processor 2 get the old value 5? Okay, so there are all of these issues here that come into play, and the bottom line here is that without coherence, processors can see different values of memory at different times, and they may get stuck that way. Like if processor 1 is in a loop looking at u equal 5, it may never get notified that it's changed. Okay, so a lot of the stuff that you think might be reasonable won't work well on a buggy processor. Now, fortunately, there are ways to fix this, and people aren't going to give you a buggy processor, you hope. But how do you fix this with a bus? Well, the nice thing about a bus is a broadcast media, so whenever processor 3 does an update, all it has to do is tell everybody on the bus, hi, I changed U, and then every cache can invalidate, thereby forcing all subsequent accesses to go back to memory. And at the same time, we've broadcasted, and all the processors throw things out of the caches. The u equals 7 can be put in memory, and we get coherence out of it. Okay, so that's one mechanism, one example where we actually have a broadcast media of a cache coherence protocol. I can give you whole lectures on that. We're not going to. I just wanted to make sure you understand the issue. The other thing you can see from this diagram is the process of reading data is not a simple one, right? If I read this data item, I may actually have to go all the way across the bus, grab data from memory, pull it back into cache, and then access it. Or this write might actually require me to do some broadcasts and updates to a long-distance operation before I'm allowed to complete. So this gets back to this notion I mentioned earlier that just because you've got shared memory and just because you've got data is out there and you know what its address is, doesn't mean you can get it quickly. And if you ask yourself, what is it that people got PhDs on with shared memory programs, it was trying to arrange so that the data was mostly separated and could live most of the time in the cache without a lot of communication, so you got the highest performance. Okay. Now, what's the problem, by the way, with a bus? Yes. Okay, so 2 people, yeah? So you can have 2 processors try to go on it at once, and if you've got good arbitration mechanisms, you won't get a bad result, but what does that lead to? Contention. So we get bus contention, which means that we can only have so much activity, and the bus is sort of, a fixed resource, and the more processors you add, the less of that resource is available, and so you can only use so many processors on a bus. Okay, and by the way, capacitance is not your friend here. So what happens? Well, people have designed, people can get 64 processors pretty easily with good pipeline buses, but how do you go scalable? Well, what you do is you build directory-based coherence, which I'm not going to go into, but you could have too much more, but you could have a generalized network that's not a bus, and all you have to do is you keep track of everybody that's got a read copy of some item so that when somebody goes to do a write, you can broadcast to them and invalidate before the write happens. And so this directory is a way of keeping track of where all the read copies are in the system. Okay, and their whole paper is on directory coherence. And this is a way of basically being able to get coherence without having a bus. Okay. The last thing I want to say here is that coherence is not enough. Okay? It may be nice that when you write a value, all the other processors see that, but it turns out that's insufficient. So everybody take a look at this code. So somebody tell me, what is this code supposed to print? Suppose that both A and flag, that says ag, but it's supposed to be flag. So flag is 0 initially. What is this code supposed to print? 1. Okay, 1. Why? Well, the reason it's supposed to print 1 is this guy is busy spitting looking for flag equals 0, and we know that processor 1 first, I say first in quotes, writes a 1 into A, then it sets flag equal to 1, so therefore when this guy finally notices that flag isn't 0 anymore, when it goes to print A, it gets back 1. Everybody on board with that reasoning? Is that correct? Yeah. So you put out of order execution into this. Suppose that you don't put out of order execution into this and you force your out of order execution to still do things in order. Is this going to get the right answer? Not necessarily, okay? Because if we have that generalized network that I mentioned, you could have updates going in different directions in a way that A takes longer to actually be visible to the system than flag, and so when P2 sees it flag equal 1, A is not updated yet. Okay? Notice that the coherence, the guarantee that eventually you see all the values, doesn't help us here. And so basically, the issue here is we need to know something about the ordering of updates with respect to more than one value at a time in order for it to be easy to program. And what I'm going to tell you briefly is this is the memory consistency model, which specifies the constraints and the order in which memory operations from any processor can appear to execute with respect to one another. So if both flag and A are written in one order on a processor, what order are they seen on the next processor? That's the consistency model. And this is also a multi-lecture discussion, so we won't do it. But I want to give you a flavor for what we could say about this. So the implications are that both the programmer and the system designer needs to know what this ordering is in order to understand their parallel programs, and you should just be aware that the consistency model might be a question you should ask. What is it? Okay? It's a contract between the programmer and the system. The consistency model I want to show you just as your baseline. This is like the gold standard of consistency models, so you can keep this in your mind. It's called sequential consistency. And the idea is that sequential consistency looks as if all of the processors that are executing can be interleaved in a way that could work on a single processor and you get the same answer. Okay, and here's this little switch view, right? Here's a physical switch, and it's kind of like I let processor 1 do something, then N, then 2, and I've got somebody busy switching that switch around, but the net effect is it's if each of them only gets access to memory in a serial way. And by the way, what I'm calling memory here is including all the effects of the caches as well. Okay? So there's a definition from Lamport. A multiprocessor is sequentially consistent if the results of any execution is the same as if the operations of all the processors were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. You guys got that? No? Okay, how about a picture? So here's processor 1. It's busy loading from variables. It's getting results back. It's got dependencies, that's red, which have to do with the forward order. This is the order the programmer programmed. This is processor's 2 forward order. And these little green dependency arrows are because this store of 6 to A flows to processor 2 to cause this load of A to give 6. Okay, so I've got 2 types of dependencies here. Program order dependencies and data flow dependencies. And what sequential consistency says is take any execution, I can always topologically resort it into a serial sequence that respects all of the forward arrows. And if you think that through, you will see that this is your intuition of what that program was supposed to do. Because no matter what the thing does, I can always come up with a sequential order that fits it. And you can build sequentially consistent shared memory multiprocessors with arbitrary networks that have distributed directories, and you can do it. Okay, I built such things. They work fine. Okay, and the nice part about this is it's easy for the programmer to think about. But that's only true if the programmer is thinking about assembly language. And so if you were to talk to Kathy Yellick or any of the others that are going to be here later in this course, and they were asked them about sequentially consistent memory systems, they would probably tell you, well, yeah, but by the time you put the compiler on it and out-of-order execution and all that sort of stuff, it doesn't matter what the hardware was doing. You don't get the sequentially consistent view anyway. And so there are many levels of sequential consistency, or many levels of consistency. Excuse me. You can talk about what the hardware provides you. You can talk about what the compiler provides you. So if you look at the Java spec, or if you look at C++, I think is well-defined. There are well-defined memory consistency semantics that you would see if you have different operations happening on different processors. But what I wanted you to be aware of is that such an idea exists, and you should look for it if you're ever going to write a program that depends intricately on the orderings of things. Okay? Are there any questions on this? Good. So what about synchronization? Okay, I can't leave shared memory without talking a little bit about synchronization. So all shared memory programs need synchronization because communication's implicit. All right, when you write to variable A on processor 1 and you read back from variable A on processor 2, that communication is implicit. There was no send data, receive data, right? It was just, I wrote here, I read there. And it turns out that this is, in some sense, the Achilles heel of shared memory because it requires you to then make up for the fact that you don't know when communications have actually happened. That's what synchronization comes into play. And we have several ways of dealing with this. We've got mutexes, which are mutually exclusion locks. So for instance, where we might say something like, grab a lock, access the data, unlock. I showed you that earlier. We've got barriers where everybody does something and everybody hits a barrier, which basically says wait until everybody's done with phase 1 before we go on. Okay. Other options are basically something like transactional memory, where this is several sort of parallelism projects are assuming the future will be all transactional memory. I'm not sure we agree with that, but the idea there is every write to a data structure is like a transaction that can be aborted if you get conflicts. Okay, and that again is a whole set of lectures I don't want to go into. But so mutexes in POSIX threads. So how do we create a mutex? There's an app for that. Oh, I'm sorry. Basically, there are ways of computing mutexes. Okay. How do you use them? Well, you could do something like this: pthread mutex lock. Okay. So notice that I've created a lock called a mutex. Now I'm locking. Okay, and I'm unlocking. Okay. How do we deallocate it? So there's ways of deallocating mutexes as well. Okay. So if you decide to choose pthreads later today, or whenever your lab is, I'm sorry, I don't know the full schedule, you could use pthreads this way, and you probably use mutexes. Okay. What are some pitfalls with locks? Well, if you don't pick the right granularity for your locks, you got problems. So here's an example where I acquire a lock, I load my S into temp, I release the lock. Then I increment temp without being inside of a lock, and then I reacquire before I store back to S. All right, well, I'll tell you, this won't give you what you expect. Okay, because I can still interleave multiple processors in the middle of this sequence. So the only way to do this correctly is acquire, say, S equal temp, temp plus plus, temp to S, and release. Okay. Another problem is deadlock. Look at here. Thread 1 grabs lock on A and then lock on B. Thread 2 grabs a lock on B, then a lock on A. There's a cyclic dependency on locks, and you are deadlocked, and you will not get out of it. Because just think, if thread 1 happens to grab lock A at the same time thread 2 grabs lock B, they're now stuck. Okay? Yeah. You like shared memory programming yet? So, performance pitfall. Critical region is too large. Here's a different problem. You grab a lock, you compute pi to the last digit, you release the lock. Okay? That's problematic, especially the compute pi to the last digit part. But what's problematic about it is the region for the locking is so big that no other processor ever gets to compute. Okay? So you got to use different locks for different structures. Okay? And of course, locks might be expensive. If you actually have to do a system call and go into the operating system to get a lock, it's probably an expensive thing to be grabbing a lock all the time. Things to be aware of. So let's also look at barriers. Okay? So here's, I showed you this earlier, work on my subgrid, barrier, read neighboring values, barrier, etc. We could do lots of different types of barriers. I just wanted to show you barriers in POSIX threads. There's a way to increment or to grab a barrier and initialize it. So this is initializing for 3 threads. And then we could do this, where every thread executes pthread barrier wait. And what happens semantically is each thread goes into the barrier wait, and they don't exit from the barrier until all 3 of them have arrived. Okay? So let me just show you, are there any questions on that? The barrier allocation use is very simple. I just wanted to make sure you saw it. Now, of course, you could get into a performance pitfall here, too. So, for instance, if you take actual computations, you could represent them as DAGs, right? This looks kind of like my sequential consistency diagram earlier. So here's Cholesky and QR factorizations. And a very common way to do some of these linear algebra type operations is you do a bunch of stuff, everybody hits a barrier, you do a bunch of stuff, everybody hits a barrier. So you can factor things in that way. Okay, that's an SPMD style of programming, which is very common. But you could, as a result of that, end up with too many barriers. So here is a scheduling that's based on barriers for those types of programs I showed you earlier. And here is a scheduling where I don't use barriers, but I rather individually schedule the data flow graph in a way that just makes sure I have everybody who produces something is weighted for by the people consuming. So you can see that barriers have this problem that they could end up wasting a lot of time, which is this white space waiting for threads to come into the barrier. Okay, good. So if you were in my hardware class, hardware architecture class, we would talk about atomic primitives. I just want you to know that you can't really build good synchronization without some sort of atomic primitives. If you try to build synchronization out of purely loads and stores, it gets messy fast. This is the most common type of synchronization, which I'd call a test and set instruction. And notice that the meaning of this is that this is atomically, this happens, where I load a value from an address, I store a 1 into that address, and I return the result, and that's all atomic. So the act of storing a 1 into the value and loading what was there prior to that store at the same time can't be interrupted by anybody. Right? And there are several others. There's things like swaps and compare and swaps and so on. And if I have that test and set, then I can actually build a lock very simply, where I just say we start out with the lock equal to 0, and everybody who wants to acquire just does this loop, while test and set value. And the idea here is the first one to do that will store a 1 and read a 0, and they'll exit the while loop and they'll have the lock, and everybody else will store a 1 and get back a 1, so they'll be stuck. Okay, and how do we release? We just store a 0, and then it's a free-for-all, and somebody in one of these while loops gets the lock. Okay, I will tell you that without a test and set, you can't build good locks. Okay. So problems here, of course, are busy waiting. So this guy is, when you're waiting for the lock, you're busy spinning and using power and computer cycles. It's also unfair because the processor that happens to be closest to the memory is more likely to get the lock than somebody far away from the memory, because like I said, there's a free-for-all. And it's also expensive because if you have cache coherence, test and set's actually a write. And so everybody's write. And so what's happening is you're broadcasting essentially invalidations to everybody. And so if there's a cache involved, it's really expensive. Okay? But this works. It's just not great. Okay? Better things are you read it first and then you do the test and set and so on. So there are many ways to make this work. But I just wanted to have you aware that without something like test and set, you can't really build synchronization well. Okay. And so finally, this busy wait versus blocking, you could, for instance, spin, like I showed you there, wait, go down. That's wasting processor cycles. Okay? Blocking is check, oh, I don't have it, go to sleep. Potentially expensive. So the thing about spinning is you can come out of it very quickly. The thing about blocking is it takes a long time to put you on a sleep queue. What's the right combination? Well, you build a hybrid, which you spin for a while, and then when you've spun for too long, you go to sleep, and it's no worse than 2 times as bad as the best option had you known the future. Okay, so you can do things like that. Now, fortunately, you guys, this is usually buried in your lock primitive, so you won't have to worry about it. Okay, so that's all I'm going to say about shared memory, and then I have one last topic. Are there any questions on the shared memory front? No? Okay. So last, I said shared memory message passing. I'm going to talk about message passing, but message passing is much easier. Okay? So here's the model for message passing. You got a bunch of processors. There's a network. The processors have all their own memory. There's no shared memory. They communicate by sending messages to one another. Okay? So a program consists of a collection of named processes. Usually you fix them at program startup, but that's not required. There's no shared data, so the only way to get data that's used by different processors is to send it. So now as a programmer, suddenly it's not like the shared memory is out there. It's like I've got a chunk of memory and somebody needs it, I better give it to them. So notice you're coordinating your communication a lot more in the message passing style. Okay? So you might actually say that by its very nature, it seems like message passing is more difficult than shared memory to get right. Now, fortunately, I saw a few people kind of shake their heads, right? Did I scare you off of shared memory a bit? You got to get the locks right, you got to get the barriers right. Well, if you don't get the barriers right, maybe you got wasted time. Oh, wait, but if the shared memory is too far away. It's a lot of questions there because there's interactions between all the hardware caches and all that sort of stuff. Message passing has none of that stuff because it's like a single processor sending data explicitly. So you as the programmer get to coordinate everything. So that's a good thing. It turns out it's a lot more code typically to write a first version of a message passing program than a first version of a shared memory program. But if you take the highly tuned version, then it's not clear because you add a lot of stuff to the shared memory version to get it to perform well by the time you're done. So I think it's 6.5 of one, half a baker's dozen of the other, as I said earlier, right? Now, MPI is a common message passing version interface, and that's used pretty commonly on the big machines up at the labs and so on. And so the idea here is that some processor is going to ask P1 to communicate, so it starts by doing a send, and then P1 does a receive, and the net result is that P1 has some data that it needs, and it goes forward. Now, here is a possible solution where each processor is going to try to compute A of 1 plus A of 2, and notice what I'm starting out is I'm assuming that processor 1 has got A of 1 and processor 2 has got A of 2. So notice that I've explicitly partitioned the memory space already. Every processor has its own chunk. Okay, that's different than shared memory. Okay, and how do we let each processor compute A of 1 plus A of 2? Well, processor 1 takes A of 1, it sends it to processor 2, it receives something from processor 2, and then it does its little sum, x local plus x remote, and processor 2 does the same thing, and when we're done, they both have A1 plus A2. Now what could go wrong here, of course, is that if send and receive act sort of like a telephone system where you have to set up a connection with send followed by receive, you see the deadlock here? This guy is trying to set up a send and this trying to set up a send, and neither of them sets up a connection. There are actually some message passing systems that require such explicit communication. Fortunately, most of them don't. Most of them act more like the messaging mailbox model, where this guy's send goes into the network, this guy's send goes into the network, and then they can do their receives later because they've been queued. Okay, but that is something that you may have to worry about in your message passing code. Is there queuing in the system, and will it deadlock me if I'm not careful? Here is a flip version of this, where you do the send and you match it with a receive on the other side, and they're explicitly lockstep, and that might be required if either your language or your network required you to set up a full connection. Okay? Now, of course, if there's more than two processors, you can start to see this gets complicated, right? Okay. So MPI is kind of the de facto standard for message passing. Most people try to compare their way of programming with MPI and say, look how much faster I am. The reason MPI has been around for so long is somebody wanted to have something that could be used on a wide variety of machines. So MPI is like a compatibility layer. It's not always the most efficient way to use a machine. But here's an example, and I'm going to go into much less of this than I did with Pthreads. But for instance, you might do something like this, where you create a buffer and you do an MPI send, and that's going off to a particular place, and then on the other side you do an MPI receive and you get your data back. You sort of are passing a buffer to the send and you're passing a buffer to receive, and the net effect is you get data. Assuming that the sender doesn't encounter a blocked network and the receiver doesn't encounter an empty network, then you're good to go. Okay. Pros and cons. So MPI is a very complicated standard. but it's pretty portable. But unfortunately, since it's sort of a least common denominator, it's definitely not your most efficient use of message passing on a piece of hardware if you choose to really go down to the assembly language. So what are some details? So all data layout in a message passing code has to be handled by software. Message passing has very high software overhead in the sense that you're explicitly deciding how to package up every message, explicitly deciding who to send it from. You can see the software overhead. Okay, so this notion of marshalling your data, you got a bunch of floating points and a bunch of strings and a bunch of integers, you got to package it up into some format, you send it in a message, it goes on the other side, you unpack all that stuff into your local variables, you use it. Okay. Now, there is a style of message passing called active messages, which became popular 15 years ago, which is basically the message not only includes data, but it also includes a pointer to a piece of code. And you send the message to another node. The node takes the message, pulls the code out, and starts executing the code. So the message itself is active. Okay, and this is a type of very high efficiency data layer that's often supported by a lot of message passing machines today. And so perhaps you'd be using an active message abstraction instead of MPI under some circumstances. Just to give you a little hardware as we're sort of winding down here. So for instance, a simple way to do message passing might be, in addition to your processor, you might actually have a special message processor, that's what MP stands for, that are both on the same bus. So this is like a local node that sends and receives into some generalized network, and then every processor kind of looks identical to this. And so what's involved in sending data? Well, what's involved is you have to actually package things up in some memory descriptor, which you hand off to your message processor, which then sends things, and then the data comes in, and your message processor puts it into memory with DMA, and then it causes an interrupt, and the processor gets it. So you can see there's a lot of potential steps there. Those of you who might know something about operating systems and TCP/IP might recognize this as well. Perhaps there's actually, this is the Ethernet board or something. Okay, there's a lot of this kind of hardware that's in standard machines as well. Okay, here's something in a machine that I designed a few years ago where it doesn't have to be that way. So here, the way you send a message is you describe the message by sort of putting a header that says where it's going. You put some data in it, and these writes are just like register writes, write. And then you say send, and poof, it goes off into the network. And then receive, what happens is you actually get an interrupt, a user level interrupt at the receive side, and all that has to happen is the receiver at user level pulls data out of the receive buffers, and you get it very rapidly. So you can have a few instructions to send and a few instructions to receive. And so you could either have this, where you've got multiple crossings of the operating system and interrupts and DMAs, or this, which is very special purpose fine-grained hardware. Those two, are different sides of the spectrum. Okay. Now, one thing that's kind of interesting is this. Here's a deadlock scenario. Okay, I always like deadlock scenarios, where what we have is we have two threads, and what each thread is doing is it's pulling something off the network, processing it, sending a response. Notice the deadlock loop, right? Anytime you see a loop, you've got to get worried. So here's a situation where if the network is completely backed up, this guy can't pull the packet off to send because it can't send. Same with this guy, and it's deadlocked and you never move forward. So anytime you have request-response like that, where you pull a request in and you produce a response, there's a potential for deadlock. There's a lot of papers written on this as well. What's the simple fix here? Anybody know? Say again? Okay, there's even a simpler one than that. Multiple networks. So multiple virtual channels basically give you essentially what look like two completely independent networks. And if you have two completely independent networks, then you know that as long as the responses are always fully received, you have no cycles here. And so with two networks, you can guarantee that request responses never deadlock. Okay? So a lot of message passing only machines, if you look in the spec, you'd see they've got two networks at least. Okay? Cache coherence protocols, remember I sort of touched on that with directory protocols earlier, may need 3 or 4 networks if they're designed poorly to avoid deadlock. So that's another interesting thing, which I'm happy to talk to you about offline. So which is better, shared memory or message passing? Depends. Okay, both are what I would kind of jokingly call communication Turing complete, which means you can build shared memory with message passing, and you can build message passing with shared memory. In fact, most shared memory machines are built on top of hardware message passing. So the machine I designed a few years ago, we said, oh, most shared memory machines are built on top of message passing. Therefore, what we'll do is we'll provide both the shared memory and hardware, and we'll give you a message passing interface that goes to the underlying network, and it's fast. We'll give you both. Okay. What are the advantages of shared memory? The communication's implicit. You don't have to package everything up. Very low overhead when you successfully get things in the cache. If you make your computation work well and things go in the cache, boy, it's fast. Because how do you send? Store. How do you receive? Load. Isn't that wonderful? Now, of course, disadvantages. Well, if you want to build hardware shared memory, it's hard to get it to scale to lots of processors. It's doable, but that's hardware complex. But you as programmers don't have to worry about that. You have to do synchronization. Ouch. Okay, that gets messy to get right. There'll be lots of discussion in our debugging and sessions later about how to, catch data races and so on. And it's very hard to control the data system, the data placement, because the way data gets placed is on demand. Because you use some locality, the data gets pulled from over there into your cache. Okay, problematic. What are the advantages of message passing? The communication's explicit. You know when a message arrived. You sent it, it arrived. Oh, I know, the data's there, everything's complete, right? So it's explicit. No synchronization needed other than the messages. It's very easy to control data placement because you put it exactly where you want it. Disadvantages? It may be very expensive in raw instructions to actually send and receive messages. Okay? It may be complex to program because you have to worry about where every piece of data is. You can't access that array A thinking about it as, oh, yeah, it's an array A with a pointer, and A1 is 1 plus the pointer and A2 is 2 plus the pointer. You can't think that way anymore. You've got to worry about, yeah, I've got A1 through 20 here and 21 through 40 there and so on. Okay? So, are there any questions about message passing? Yes?
So I was just listening to how it's message passing versus the shared memory. The shared memory has to have the bus broadcasting changes to variables to everybody. It seems like that might be higher overhead than just sending the messages that you need to location.
So the question for so the question for focus in cyberspace as well is, it seems like shared memory requires a bus, and so therefore broadcasting everything to everybody would be expensive, and shared memory and message passing is much more directed. So the first thing I want to say is that, as I just alluded to, you don't really need a bus. So with directory protocols, you can arrange to use an arbitrary network, and then what happens there is that, let's suppose processors 1 through 5 read variable A and it's in their cache, and processor 6 goes to write. What's nice about the directory cache, or the directory for cache coherence, is it knows exactly which processors to send and validates to. So you're not broadcasting anymore. So I don't want to leave you with the thought that shared memory requires a bus, because it doesn't. Okay. However, you have hit upon a very important point there, which is the nice thing about message passing is you're directed. You're sending directly the data where it needs to go. Shared memory is trying to fake out. Remember how we started this lecture with this notion of architects were trying to fake out the programmers into thinking they had a serial stream, even though there's a lot of stuff underneath? Shared memory has the same property to it, which is I'm trying to fake out end processors into thinking there's a shared memory out there that I have access to, and it's sort of as fast as I can get at it. And the cache coherence protocols with the invalidates and the reads and the writes and all that sort of stuff going across the network is a hidden overhead. Because in order to, let's take a very simple example. Processor 1 writes, processor 2 reads. What really happens? Well, processor 1 goes to write. A write request goes to the directory where the value is stored. The directory says, okay, you can write. It writes. Processor 2 reads. It goes to the directory. The directory says, oops, goes to A, please give me your data. A comes back with the data, then it goes back to B. It's processor 2. So notice how what happened there was we had sort of 1 round trip, 2 or 3 round trips just to go send data from processor 1 to processor 2. In the case of message passing, it goes from processor 1 to processor 2. So the shared memory is trying to hide something from you. It's trying to hide the locality properties of where the data is. And as a result, from an efficiency standpoint underneath, it's much less efficient. And the question is it more convenient and can you mostly hit in the cache? And if the answer is more convenient or you can mostly hit in the cache all the time, then shared memory is going to give you better performance. Okay? I mean, it is kind of interesting because when you start really trying to tune things, then you really start worrying about, well, what's really going on underneath? And shared memory starts to look pretty bad when you start looking at all the messages flying around. But why is it so complicated? Because it's trying to provide an abstraction of shared memory to people that they don't have to worry about. Okay, good question. Are there any other questions? Yes?
Through techniques like pipelining, we should be able to hide the efficiency loss because of the message passing. You could pass the message while...
So pipelining, so in principle, pipelining can hide all sorts of sins. However, the same thing that got the hardware architects in trouble with pipelining, namely hazards, in principle come up here as well, which is, yeah, you can pipeline messages and get them going out, but the question is, at what point do you need the response back before you can make progress, and then you'll be blocked. And so the way a lot of these SPMD algorithms, I'm going to throw out single processor, multiple data algorithms, are really ones with phases. Phase 1, barrier, phase 2, barrier. And what the phases do is each phase, every processor sends a bunch of stuff, barrier. Each processor receives a bunch of stuff, computes, sends a bunch of stuff, barrier. And so effectively the programming style there is, you could say, introducing pipelining into the programming in a way to try to overlap the message communication. So you're exactly right, but it's only if your algorithm supports that. So that's good. Now, of course, this was the optional part. I had a bunch of interesting machines to show you, which is fine. We can come up afterwards. But here's a bunch of configurations for processors, including processors on a bus, processors with a general network, processors kind of on a regular network. Things like T3E and so on, which you guys might actually be using. 3-dimensional meshes with processors, message passing. Okay. Here's another Cray processor. What I wanted to show you as well, let's do a couple of these and then we'll close up. Oh yeah, here's the Alewife, which is that machine I mentioned earlier that does both message passing and shared memory. This is very dated now. Here's the J machine. This was an experimental message passing machine back in the early 90s that had 1,024 processors in a 3-dimensional mesh. Okay, so people have been building these things for a long time. Have they been able to program them? No, that's a whole other story, right? So here we'll close up with this. This is what we're about in these lectures. Multi-core. Here's Intel, here's AMD, lots of cores, all on the same chip. Okay, this is an interesting new style of parallelism. Okay, where the latencies are much shorter than they were if you had to go off chip. The power to go off chip is not there because you're talking cross purposes. And the real question is, can you make advantage of these or not? Okay, take advantage. All right, so let's finish. I told you about uniprocessor parallelism. Don't get me wrong, people are still doing it. Okay, your multi-core chip you buy from Intel has got out-of-order execution in it. Okay, but multiple processors. There's multi-threading, which I started with simultaneous multi-threading. I showed you Pthreads as a style. There's the memory system point, which is important to realize that if you don't remember what's happening with your memory system, you're likely to get poor performance. We talked about shared memory, and we talked about message passing, and I'm certainly happy to be available for questions afterwards. But I think we'll close. And that clock is actually a little fast. But anyway, sorry about that. All right. And I don't know what the rest of the schedule. We have lunch now for people, or what's this?
Yes.
Okay. Great. All right. You're off.
So before you go off...
Oh, you're not off. Thank you.